In this lesson, the brake modulating and automatic braking systems, as fitted to most modern airliners, will be described. Brake modulating systems are normally referred to as anti-skid systems. Optimum braking is important in the operation of modern aircraft, with their high landing speeds, low drag and high weight, particularly when coupled with operation from and into short runways in bad weather. The pilot is unable to sense when the wheels lock, and so the primary requirement of a brake modulating system is to provide skid prevention. Whenever braking torque is developed, there must only be a small degree of slip between the wheel and the ground. A skidding wheel provides very little braking effect. In all brake modulating systems, the deceleration of the individual wheels is taken as the controlling parameter of braking torque. A datum figure for wheel deceleration is selected, which is known to be greater than the maximum possible deceleration rate of the aircraft. When this datum figure is exceeded, brake pressure is automatically reduced or released. Systems may be mechanical or electrical. Mechanical systems have been in use since the early 1950s. Most aircraft today use electrical or electronic systems. Anti-skid systems have a huge effect on the distance required to bring an aircraft to a stop from high speed. The required stopping distance increases considerably if the anti-skid system is unserviceable. An electronic anti-skid system comprises three main elements: a sensor, which measures wheel speed, a control box, known as an anti-skid unit or ASU, to compute wheel speed information, and a servo valve or anti-skid valve to modulate brake pressure. The anti-skid unit provides three important functions. These are touchdown protection, skid prevention, and locked wheel protection. Touchdown protection prevents the brakes being applied before touchdown. The electronic anti-skid unit will monitor the wheel speed and air-ground logic. If no signal is received, the brakes cannot be applied while the aircraft is airborne. On touchdown, the wheels spin up and apply a signal to the control unit, which will now allow the brakes to be applied. This does not, however, imply that you should attempt a landing with the brake pedals depressed. It is a safety backup system only. For skid prevention, the anti-skid control unit will reduce the brake pressure to any wheel that it determines is approaching a skid by monitoring the deceleration rate of the individual wheels. It will then modulate the pressure to ensure optimum braking. Most electronic anti-skid units have an adaptive pressure bias modulation circuit. This ensures that with the pilot applying a constant pressure on the pedals, the brake pressure applied immediately after a wheel is released following a skid is lower than the pressure which caused the skid. This prevents an immediate return to the skid conditions that caused the anti-skid unit to release the pressure in the first place. If a wheel locks because of a wet patch or ice, for instance, the anti-skid controller will release the brake pressure to that wheel completely until the wheel spins up again. Then the pressure will be reapplied. This feature is usually disabled at low speed. A brake torque sensor is provided at each wheel to detect excessive torque during braking, to prevent damage to the landing gear strut or strut mountings. This is more of a problem with carbon brakes. When excessive torque stress is detected, a signal is sent to the anti-skid valve, and brake pressure to that wheel is reduced. To enable the pilot to have full control of the brakes for taxiing and manoeuvring, on some aircraft types, the anti-skid system is automatically deactivated when the aircraft has slowed down to below approximately 10 knots, when it is assumed that there is no further danger of skidding. To summarise the electronic anti-skid system, here is a demonstration of how it will operate during approach and landing. On approach, with the gear selected down and anti-skid switched on, the touchdown protection system will not allow the brakes to be applied. On touchdown, once the ASU receives an on-ground signal and the main wheels have spun up to about 80 knots, touchdown protection is disabled and braking can commence. The anti-skid system will now modulate the brakes to produce optimum braking. Should any wheel lock for any reason, then the locked wheel protection system will completely release the pressure to the locked wheel until it spins up again. As the aircraft slows through about 20 knots, the locked wheel protection system is disabled. Finally, on some systems, as the aircraft slows through about 10 knots, the entire anti-skid system is disabled, and braking is completely in the hands, or more correctly the feet, of the pilot. Most modern aircraft have an automatic braking system which can be selected to operate during landing rollout or during a rejected takeoff. The auto brake system is usually only usable when the brakes are being supplied from their normal hydraulic source. It is not normally available when using the alternate brake system. The main advantages of such a system are that it will react more quickly than the pilot, and will also constantly apply the correct amount of braking to provide the required rate of deceleration. Depending on the aircraft type, a number of landing deceleration rates may be selected. The Boeing system shown here uses a rotary selector switch to control the level of braking required. The rejected takeoff or RTO selection provides maximum braking. On an Airbus, push buttons are used, with max being selected on takeoff to give rejected takeoff protection. The decel lights illuminate during the landing roll to indicate that the selected level of deceleration is being achieved. Anti-skid protection is provided during auto-brake operation. If the anti-skid system is unserviceable, then the auto-brake system is disabled. On systems with a rotary selector, the landing auto-brake system is armed by selecting one of the deceleration rates on the auto-brake selector. The system is now armed, provided the anti-skid system is serviceable and the normal brake system is being used. If these parameters are not met, then the auto-brake disarm light will illuminate. On touchdown, with ground mode and wheels spin-up sensed, the brakes will be automatically applied and will slow the aircraft at the selected rate of deceleration to a complete stop, or until the auto-brakes are disarmed. The deceleration rate may be changed during auto-brake operation without disarming by rotating the selector. With RTO selected, maximum brake pressure, modulated by the anti-skid unit, will be applied automatically when all thrust levers are closed, at ground speeds above a specific speed depending on aircraft type, normally around 85 knots. This brings the aircraft to a stop in the shortest possible distance. If a rejected takeoff is initiated below this specific speed, the auto-brake system will not be activated, and manual braking will be required. The pilot can disarm the auto-brake at any time and revert to manual braking simply by applying pressure to the brake pedals. As we have already seen, the auto-brake system disarms immediately, and the disarm light will illuminate if an auto-brake or normal anti-skid system fault occurs, or if manual braking is applied. During auto-brake operation, disarming will also occur if after landing any thrust lever is advanced, or after landing if the speed brake lever is returned to the down detent after the speed brakes have been deployed. This is because advancing the thrust levers, or retracting the speed brakes, is an indication of a rejected landing. The auto brakes can also be disarmed by moving the auto brake selector to disarm or to off. In this case, the disarm light will not illuminate. However, the auto brake system is normally disarmed by the handling pilot tapping the brake pedals, when he is happy that the speed of the aircraft is under control. That is the end of the lesson on anti-skid and auto brake systems. Remember that a modern anti-skid system, as well as producing optimum deceleration, also has the additional features of touchdown protection, preventing the brakes being applied before landing, and locked wheel protection, releasing the pressure to any wheel that locks because of hitting a very slippery patch on the runway. The auto brake system, if armed before landing, will automatically apply the brakes after touchdown and decelerate the aircraft at a predetermined rate. If the rejected takeoff mode is armed, in the event of a rejected takeoff, it will stop the aircraft in the shortest possible distance. This lesson will explain the operation of the parking brake, and then we will look at the components that make up a typical hydraulic braking system. The brake kinetic energy graph will be described, as will the brake temperature indicating system. The parking brake is used to maintain pressure at the brakes when the aircraft is parked without chocks. Normally, once chocks are fitted, the brakes can be released. The parking brake is not a mechanical device such as is found on your car. It requires hydraulic power to apply and hold the brakes. The parking brake lever is spring-loaded to the off position. To apply the parking brake, the foot pedals are depressed. Then the parking brake lever is pulled. Whilst holding the lever in position, the pedals are then released. This allows the latch pin on the pedal mechanism to engage with the pawl on the lever mechanism, locking the pedals down and the lever in the engaged position, thus keeping the brake metering valves open, applying full pressure to the brakes. An electrical switch connected to the parking brake lever operates when the lever is in the engaged position, closing a valve in the anti-skid system return line, preventing fluid bleeding away from the brakes. A fully charged brake accumulator will have sufficient fluid to hold the brakes fully on overnight. To release the parking brake, the pedals are depressed, allowing the lock pin to release from the pawl and the lever to spring forward. The typical wheel brake system shown here has all the features and components we have discussed so far. The brakes are normally powered by one of the aircraft hydraulic power systems, System B, with automatic switchover to an alternate system, System A, in the event of low pressure in System B. When both normal and alternate brake hydraulic sources are unavailable, an accumulator will maintain pressure to the brake system. The accumulator pressure gauge is on the gas side of the accumulator. Provided hydraulic system pressure is available, it will read system pressure. However, if normal system pressure is lost and the brakes are operated, the accumulator pressure will fall until all fluid in it is used up. The gauge will then read the gas pre-charge pressure. The non-return valve will prevent backflow to the pumps. In some systems, the accumulator has sufficient fluid to stop the aircraft from high speed, but in others, it only has sufficient fluid to maintain the parking brake overnight. There are shuttle valves placed between the manual and auto brake systems. These will move across to allow whichever system is supplying the highest pressure to supply the brakes. The hydraulic fluid from the brake metering valves, or the auto brake valve, passes freely through the anti-skid valves to the brakes, unless an incipient skid is sensed by the anti-skid system. Wheel speed transducers mounted in the axles transmit wheel speed inputs to the anti-skid control unit. Each wheel is provided individually with anti-skid protection. When skidding is initially detected, The anti-skid controller adaptive pressure bias modulation circuit commands the respective anti-skid valve, firstly to release the brake pressure, then to apply a reduced pressure to protect the wheel from further skidding. Many aircraft have a system fitted whereby whenever the landing gear is selected up, the wheel brakes are automatically applied to stop the wheels rotating in the wheel wells. During the application of brakes, a considerable amount of energy is absorbed. This energy is released in the form of heat, which must be dissipated. The brake packs, wheel assemblies and tyres are capable of absorbing a certain amount of heat before they fail. Some method of determining the amount of energy absorbed will facilitate decisions regarding precautions and actions to be taken after an aborted takeoff, a landing, or simply taxiing the aircraft around the airfield. One such method is the brake kinetic energy graph. A graph similar to this one will be found in your particular aircraft performance manual. The graph is entered with all up weight and brake application speed in knots, corrected for wind, and then factored for the number of serviceable engine thrust reversers and airfield altitude. The graph will then indicate the amount of kinetic energy absorbed in millions of foot-pounds. This figure is not of much interest to pilots. However, the graph output is also split into 3 zones: the normal, caution and danger zones. It is these zones and the actions and precautions associated with them that the pilot is interested in. The actions and precautions for the 3 zones are listed here. You can take a moment to read them, but bear in mind that they will vary from aircraft type to aircraft type. As an example, we will use an aborted takeoff at a weight of 280,000 pounds, stopping from a speed of 125 knots, with no wind, and 1 reverser operating at an airfield with a pressure altitude of 2,000 feet. The graph is entered with the weight, 280,000 pounds. We move across to the reference line, then up the guidelines until the 125 knot line is intercepted. We then move across to the reverser's reference line and up to intercept the 1 reverser operating point. We now move across to the altitude reference line, then up to intercept the 2,000 feet point. Finally, we move to the right to read off the brake kinetic energy absorbed, 27 million foot-pounds. As this was an aborted takeoff, Note 2 applies, meaning we need to add 5, which brings it to 32. So, we are in the danger zone. Many aircraft are fitted with brake temperature indicators. Older aircraft have electromechanical indicators, while on more modern aircraft, the temperatures can be displayed on one of the electronic display screens. Sensors are arranged to sample the temperature of the brakes of each individual wheel, and their output is sent to the indicator panel. Here, you can see a system typical of that used on many older aircraft. The indicator has 2 pointers labelled left and right. This particular aircraft has 4 wheels on each bogie. They are represented on the group of 4 mechanical push switches, only one of which can be depressed at a time. Each switch allows the brake temperature of a pair of wheels to be displayed on the indicator. For instance, if the left forward push button was pressed in, then the gauge would now be reading the temperature of the front pair of wheels on the left bogie. The brake temperatures of all wheels are constantly monitored by the system. If the temperature of any brake assembly rises above a predetermined level, then an amber high temperature indicator light illuminates. By cycling through the switch positions, the operator will be able to locate the wheel brake which is triggering the alarm. Should any brake temperature go even higher, there is another trigger point at which a red brake overheat caption will illuminate. On aircraft with a central warning system, the brake overheat warning will normally be repeated on it. There is a push button for testing the system. When it is pressed and held, the indicated temperature for the selected pair of wheels will rise by about 100 degrees. Shown here is the system used by Airbus. All of the landing gear information is brought together on one electronic screen. The brake temperatures normally appear in green, changing to amber with a caution light if the temperature exceeds 300 degrees Celsius. This system also has the facility to monitor the anti-skid system. The bars appear when the system is armed, and the release annunciations appear when the anti-skid is operating and releasing brake pressure. Brake temperature indicators are a useful guide for the crew. However, after heavy braking, in the event, for instance, of an aborted takeoff, it can take some considerable time, 10 minutes or more, before the energy absorbed by the wheel, tyre and brake assembly manifests itself on the temperature gauge. It is important that in such a case, the brake kinetic energy graph is consulted before a course of action is decided upon. There are a number of aids available to you, the pilot, to help you bring the aircraft to a safe stop on a limiting runway in marginal conditions. However, these all need to be used correctly. A safe stop begins with a good landing. This means using the correct approach speed and touching down at the correct place on the runway. Full anti-skid braking should be applied immediately after touchdown. Do not use cadence braking. That is to say, do not pump the brake pedal up and down. The ground spoilers should be immediately deployed, not so much for their stopping assistance, but more for the fact that they dump the lift from the wings, putting more weight on the wheels, allowing the brakes to operate more efficiently. Finally, reverse thrust should be selected without delay. The aim of this series of lessons on flight controls is to describe the various primary and secondary flight controls that are available to you, the pilot, and to explain the mechanics of how the pilot's flight deck inputs cause the controls to move. The aerodynamic reasons why flight controls have the effect that they have on the aircraft is outside the scope of these lessons. We will only touch on the theory here when it is necessary for reasons of clarity. In this first introductory lesson, we will look at how an aeroplane moves around its axes. For steady flight, the aircraft must be in a state of balance, with zero moments around its axes. The primary flight controls are designed to enable this to be achieved for all possible configurations and centre of gravity positions. The controls are also required to manoeuvre the aircraft around its three axes. The three axes about which an aeroplane rotates are the lateral axis, the longitudinal axis, and the normal axis. The movement around an axis is produced by changing the aerodynamic force on the appropriate aerofoil, wing, tail or fin, and this may be done by changing the camber of the aerofoil by deflecting a control surface, changing the angle of attack or incidence of the aerofoil, or decreasing the aerodynamic force by spoiling the airflow. The most common method used is to change the camber of the aerofoil, This is done by deflecting a control surface on the trailing edge of the aerofoil, either up, decreasing the camber and the amount of aerodynamic force generated, or down, increasing the camber and the amount of force generated. This principle can be applied to control about each of the axes. The aircraft rolls about its longitudinal axis. The devices most commonly used to control roll are the ailerons. The ailerons are operated by rotating the control wheel or yoke, or by moving the control column or stick laterally. Rotating the control wheel clockwise will cause the left aileron to move down and the right aileron to move up. The aircraft will bank to the right. Counterclockwise rotation of the control wheel will have the opposite effect. That is, the aircraft will bank to the left. The aircraft pitches about its lateral axis. Pitch control is most commonly achieved by the use of elevators. The elevators are controlled by moving the control wheel or control column fore and aft. Pushing the control wheel forward lowers the elevator and the aircraft pitches down. Pulling back on the control wheel raises the elevator and the aircraft pitches up. The aircraft yaws about its normal axis. Control in yaw is normally achieved by the use of a rudder. The rudder is controlled by the rudder pedals. Pushing the left pedal forward causes the rudder to move to the left, and the aircraft nose to your left. Pushing the right pedal forward causes the rudder to move to the right, and the aircraft nose to your right. The ailerons, elevators and rudder are known as the primary flight controls. That is the end of this introductory lesson. You now know that ailerons control the roll of the aircraft about its longitudinal axis, that elevators control the aircraft's pitch about its lateral axis, and that rudders control yaw about the normal axis. In this lesson, we will discuss the primary flight controls which control and balance the aircraft in pitch. Longitudinal control is achieved by the use of elevators, which are flap-type controls normally fitted to the trailing edge of the tailplane or stabilizer. These surfaces control the aircraft in pitch about the lateral axis. The controls must be adequate to balance the aircraft throughout its speed range, at all permitted centre of gravity positions and configurations, and to give an adequate rate of pitch for manoeuvres. The pilot controls the elevators by the use of a yoke or control column. This control operates the flying control surface and is moved in a fore and aft direction by the pilot to control the aircraft. If the pilot pulls the yoke or control column towards himself, then the elevator moves up. The degree of movement of the cockpit control directly affects the angular displacement of the control surface. This movement produces an aerodynamic downforce on the tail, which will pitch the aircraft nose up. If the pilot pushes the yoke or stick away from himself, then the elevator will move down. An up force will now be produced on the tail, which will pitch the nose of the aircraft down. Varying the incidence, and hence the angle of attack of an aerofoil, will also vary its lift. This system is often used instead of elevators for pitch control. The whole of the tailplane or stabilizer is rotated to vary its angle of attack. If the yoke is pushed forward, the leading edge of the stabilizer moves up, and the trailing edge down. This increases the lift generated by the stabilizer. so the nose of the aircraft pitches down. If the yoke is pulled back, then the stabilizer rotates in the opposite direction, and the nose pitches up. That is the end of the lesson. You should now understand that control in pitch is achieved using elevators or a moving tailplane. In this lesson, we will discuss the various ways in which lateral control about the longitudinal axis of the aircraft is achieved. The aircraft rolls about its longitudinal axis. Lateral control about this axis is primarily achieved by ailerons. There is an aileron on the trailing edge of each wing. The ailerons are operated by the control column or yoke. The ailerons are flap-type controls, but their angular movements are in opposition to each other. When one aileron is angled up, the other is angled down. Consider the aircraft in the graphic. The left wing has the downgoing aileron. This will increase the camber and increase lift. The upgoing aileron on the right wing has a reduced camber, so its lift will be reduced. The lift forces are now out of balance, and the aircraft will roll to the right. It will continue rolling to the right until the ailerons are returned to the neutral position by the pilot. Movement of the control column or yoke is instinctive. If the pilot wishes the aircraft to roll right, the yoke is rotated right. Rotate the control to the left, and the aircraft will roll left. An undesirable side effect of the use of ailerons is adverse aileron yaw. The increased lift on the upgoing wing gives an increase in the induced drag, whereas the reduced lift on the downgoing wing gives a decrease in induced drag. The difference in drag on the two wings produces a yawing moment, which is opposite to the rolling moment. That is, a roll to the left produces a yawing moment to the right, and a roll to the right produces a yaw to the left. There are three main methods in common use to counteract this adverse yaw. They are differential ailerons, freeze ailerons, and aileron rudder coupling. We will now have a look at each of these methods. With differential ailerons, the aileron linkage causes the upgoing aileron to move through a larger angle of deflection than the downgoing aileron. This increases the parasite drag on the upgoing aileron and reduces it on the downgoing aileron, thus reducing the difference in total drag between the two wings. Freeze-type ailerons achieve the same balance in drag by having the leading edge of the control surface designed so that it extends below the lower surface of the wing on the upgoing aileron, thus increasing its drag. The downgoing aileron leading edge remains shrouded and produces less drag. Some aircraft may employ a control system using the principles of differential and freeze ailerons together. These are known as differential freeze-type ailerons. Not only does the upgoing aileron travel further than the downgoing one, the leading edge of the upgoing aileron also extends into the airflow. In the aileron rudder coupling system, the aileron and rudder systems are interconnected, so that when the ailerons are deflected, the rudder automatically moves to counter the adverse yaw. The ailerons are normally situated at the wingtip to give the greatest moment for the force produced. However, this also means that they cause the maximum twisting and bending loads on the wing. As the aircraft speed increases, this can cause a loss of effectiveness, or even reversal of the aileron. To reduce these effects, the ailerons can be mounted further inboard. Alternatively, two sets of ailerons are often fitted, one set at the wingtip for use at low speeds when the forces involved are low, and one set inboard for use at high speeds when the forces are greater and could cause greater structural distortion. On some aircraft, with both inboard and outboard ailerons, both sets are used at low speed. But once the flaps are retracted, the outboard ailerons are locked out and only the inboards operate. On others, the outboard ailerons are used in isolation until the flaps are retracted. The system then switches to the inboards only. The trailing edge flaps, which are discussed in another lesson, and the ailerons, both occupy part of the trailing edge of the wing. For good takeoff and landing performance, the flaps need to be as large as possible. And for a good rate of roll, the ailerons need to be as large as possible. However, space available on the wing trailing edge is limited, and one solution is to droop the ailerons symmetrically to augment the flap area. They then move differentially from the droop position to give lateral control. This method is used throughout the Airbus fleet. Another system uses the trailing edge movable surfaces to perform the operation of both flaps and ailerons. Such devices are known as flaperons. They are shown here on the SkyStar Kitfox. Spoilers are devices for reducing the lift of an aerofoil by disturbing the airflow over the upper surface. Their use is fully covered in another lesson. They are normally considered as secondary flight controls. However, they are often also used to assist the ailerons and occasionally to replace them by reducing the lift on one wing but not on the other. Raising the spoiler panels will disturb the airflow over the wing and reduce the lift. When a roll is instigated, the spoiler panels on the downgoing wing will deploy, while those on the upgoing wing will remain stowed. Unlike the aileron, spoilers cannot increase lift, and so a roll maneuver controlled by spoilers will always result in a net loss of lift. However, the spoiler has several advantages over the aileron. There is no adverse yaw. The raised spoiler increases the drag, and so the yaw is in the same direction as the roll. Wing twisting is reduced. The loss of lift is distributed across the chord, rather than being concentrated at the trailing edge. It does not suffer from the phenomenon of flutter. Flutter will be explained in a later lesson. Spoilers do not occupy the wing trailing edge, so there is more space available for trailing edge flaps. On some types of aircraft, rotation around two of the axes may be achieved with one control surface. For instance, the elevon, a combined elevator and aileron, is used on tailless aircraft to give both pitching and rolling control. The ruddervator is the name of the control surfaces on the empennage of a V-tail aircraft, which combines both pitching and yawing control. The stabilator is a movable tailplane, combining the functions of horizontal stabilizer and elevator. One of the few airliners to use a genuine stabilator was the Lockheed TriStar. That is the end of the lesson. Here are the important points you should take from it. Spoilers may be used for roll control. Remember that the panels on the downgoing wing will deploy whilst those on the upgoing wing will remain retracted. Inboard ailerons are used to reduce wing twisting for high-speed flight. The outboard ailerons are normally disabled when the trailing edge flaps are fully retracted. There are a number of methods used to counteract adverse yaw, the most popular being differential ailerons. With this system, the upgoing aileron moves through a greater angle than the downgoing one, to equalize the drag on the wing. In this lesson, we will discuss how an aircraft is controlled around its normal axis. We will also discuss the control position indicator, which is used to keep pilots informed of the position of their aircraft's flight controls. Rotation around the normal axis is yawing and is controlled by the rudder, which is normally fitted to the trailing edge of the tail fin. The rudder is required to maintain directional control with asymmetric power, to correct for crosswinds on takeoff and landing, to correct for adverse yaw, to recover from a spin, and, on a single-engine aircraft, to correct for changes in propeller torque. The rudder is a flap-type control and is controlled from the cockpit by the pilot's feet moving the rudder pedals. Pushing forward on the right rudder pedal moves the rudder to the right, generating an aerodynamic force, causing the nose of the aircraft to yaw to the right. Pushing on the left pedal causes the opposite to happen, and the nose of the aircraft will yaw to the left. With a simple control system, full rudder pedal movement will provide full rudder deflection. With high-speed multi-engine aircraft, it is necessary to have large rudder deflections available at low speed to allow the aircraft to be controlled in the event of engine failure. However, when flying at high speed, full rudder deflection would cause excessive loads on the structure. To prevent this occurrence, a gear change system, known as a rudder ratio changer, may be incorporated into the rudder control system. This may be a single gear change, which gives a smaller rudder deflection for full pedal movement above a certain speed, or a progressive gear change, which gives a decreasing rudder deflection with full pedal movement as speed increases. This graph depicts the operation of a typical ratio changer. You can see that full rudder is available up until 160 knots. The travel then reduces progressively until at 380 knots, only approximately 3 degrees of travel is available with full pedal deflection. You now know how the aircraft is controlled about its 3 axes. To keep the pilots informed of what the primary flight controls are doing, their positions are displayed on an indicator on the flight deck. There are a number of different systems used for this. Displayed here are the systems used on the Boeing 747 and on Airbus aircraft. The older electromechanical indicator for the 747 is quite simple and self-explanatory, but rather limited in what it can display. The electronic indication on the Airbus Electronic Centralized Aircraft Monitor, ECAM, on the other hand, is able to display a wealth of information. The letters beside the individual surface indicators show the status of the hydraulic systems operating the surface. They are normally green, but change to amber in the case of a failure. In this graphic, the blue hydraulic system has failed. That is the end of the lesson. You now know that control in yaw is achieved using the rudder. Also remember that modern airliners have some type of rudder ratio change mechanism to reduce the amount of rudder travel at high aircraft speed. This lesson covers the reasons for aerodynamic balance of flight controls and the various methods that are employed to achieve this balance. The aerodynamic force acting on a control surface through its centre of pressure would tend to rotate the control around its hinge in the direction of the force. The moment produced will be the force F multiplied by the distance d from the hinge to the centre of pressure. This is known as the hinge moment. The aerodynamic force will vary with the angle of deflection of the control surface, the size of the control surface, and the speed squared. The size of the control surface is usually fixed. However, as speed increases, the aerodynamic force generated greatly increases. To move the flying control surface to the required angular displacement and maintain it in that position, the pilot has to overcome and then balance the hinge moment by applying a force to the cockpit control. The cockpit control load or stick force will therefore depend on the size of the hinge moment. Up to a point, this is a good thing, as it produces feel in the controls. However, for large and fast aircraft, the resulting force could give hinge moments and related stick forces which will be too high for easy operation of the controls. The pilot will require assistance to move the controls in these conditions, and this can be done by using mechanical advantage or by power operation, both of which will be discussed in another lesson, or by using a system to reduce or oppose the moment. Modern large aircraft have flight control systems operated by hydraulic power. However, smaller aircraft will have a mechanical system where the pilot provides the motive force. Having moved the control surface, he will have to maintain a force on the control to oppose the aerodynamic force, which will be attempting to reverse the operation and return the surface to the neutral position. For this reason, manually operated flight controls are known as reversible controls. Aerodynamic balance is a common method of helping the pilot of an aircraft with manual controls to move the controls while still leaving him with a reasonable amount of feel. Aerodynamic balance involves using the aerodynamic forces on the control surface to reduce the hinge moment. It may be achieved in several ways, and we will now have a look at some of the methods used. The first method we should look at is called the inset or setback hinge. Setting the hinge back in the control surface puts it nearer the centre of pressure, causing the hinge moment to be reduced. Furthermore, the airflow strikes the surface forward of the hinge, exerting a force which opposes the hinge moment and helps the pilot move the control. Setting the hinge back does not reduce the effectiveness of the control. Only the hinge moment of the force is reduced, not the force itself. It is important that the centre of pressure is not moved too close to the hinge line, as when a control is operated, its centre of pressure moves forward. If this was to take the centre of pressure forward beyond the hinge line, then all feel would be removed, or even reversed. The principle of horn balance is similar to that of the setback hinge. The horn is part of the control surface and is forward of the hinge line. In flight, when the control surface is displaced, as shown in the diagram, aerodynamic forces will be generated both fore and aft of the hinge line. This produces turning moments about the hinge, reducing the overall hinge moment. Once again, control effectiveness is unaffected. Design of the horn balance will mean that during operation, the horn extends above or below the surface of the main aerofoil section. This will cause an increase in drag. Horn balance is commonly found on rudders and elevators. Internal balance works on the same principle as the setback hinge, but the balancing area is enclosed inside the rear of the main aerofoil section. This forms a chamber split into two halves by a flexible diaphragm, the areas of which will feel the same changes in pressure as are produced above and below the control surface. The pressure differential inside the chamber will produce a moment in opposition to the hinge moment. In our example, the control surface is moved down. Pressure above the aerofoil is reduced, and pressure below it is increased. The reduced pressure is felt on the upper surface of the balance, and the increased pressure on the lower surface. The pressure difference on the balance therefore gives a hinge moment, which is in opposition to the hinge moment on the main control surface, and the overall hinge moment is reduced. The advantage of this system over the previous two is that because the balancing area is inside the wing, there is no increase in drag. All of the previous solutions provide balance by causing some of the pressures on the control surface to act forward of the hinge line. Stick force can also be changed by small aerofoil tabs positioned at the rear of the control surface, but these do alter the effectiveness of the flying control. There are four main types of trailing edge tab device. They are the balance tab, the anti-balance tab, the spring tab, and the servo tab. These tabs are small aerofoil sections hinged at the trailing edge of the flying control surface. Their actual size will vary from aircraft to aircraft. We will now take a look at each of these tabs in greater detail. We will first consider the balance tab. The pilot has no direct control over tab movement. The pilot's inputs to the flying control are transmitted by a linkage to move the balance tab in the opposite direction to the flying control surface. The pilot moves the control surface moves the tab. The balance tab generates an aerodynamic force in the opposite direction to the flying control surface. This reduces the hinge moment and stick force, but will also give some reduction in control effectiveness. Aircraft fitted with large elevators or stabilators are capable of generating very powerful aerodynamic forces due to their large surface area. For relatively small control deflections, especially at high speeds, the forces produced could cause the pilot to over-control. If this were the case, an increase in stick force would reduce the possibility of over-controlling. This can be achieved by the use of an anti-balance tab. You can see from the graphic the similarity between a balance and an anti-balance tab. The difference is that the arrangement of the control linkage causes the anti-balance tab to move in the same direction as the control surface. It can be seen from the graphic that both the tab and the control surface force act in the same direction. Anti-balance tabs are commonly used on all flying tailplanes, otherwise known as stabilators. Remember, the balance tab reduces stick force, while the anti-balance tab increases it. The servo tab is used to assist the pilot in moving the control surface. It differs from the previous two tab controls in that the pilot actually controls the tab and not the control surface. Movement of the tab generates an aerodynamic force which moves the main flying control. View the sequence of events in the graphic, which depicts an elevator with a servo tab attached. As the pilot selects a nose-up pitch, note that to pitch nose up, the tab moves down, causing the elevator to move up. This does not affect the way the pilot operates his cockpit controls. You can use your mouse to step through the operation of the servo tab. Each click in the box will move it forward one step. If the aircraft is stationary on the ground, movement of the cockpit control will give no movement of the control surface, only of the tab. The control becomes effective as speed increases. It should also be noted that if external control locks are fitted to the control surface, the cockpit control will still be free to move, as the tab is not normally locked. Servo tabs tend to be used on larger aircraft, where the weight, due to the physical size of the flight controls, let alone their aerodynamic forces, would produce very large stick forces. The Boeing 737, for instance, normally uses hydraulic power for its flight controls, but has servo tabs as a backup in the event of hydraulic system failure. The final tab we are going to look at is the spring tab. It is a modification of the balance tab, such that the tab movement is proportional to the applied stick force. Maximum assistance is therefore obtained when the stick forces are greatest. This is achieved by putting a spring in the linkage to the tab. The spring tab is used mainly to reduce control loads at high airspeeds. The pilot's control movement is transmitted to a lever pivoted on the primary control surface, but not directly operating it. Operation of the control surface is via springs. With low aerodynamic loads, the springs are strong enough not to be compressed, so the control surface moves with control input, and there is no change in the position of the trim tab relative to the control surface. The full load is felt by the pilot. As the aerodynamic loads increase, the spring force will be overcome, causing the balance tab to move in the opposite direction to the primary control surface, thus reducing the stick forces. There is one more form of balancing that is applicable to flying control surfaces, but this time it has nothing to do with assisting the pilot to operate the controls or to reduce stick force. It is known as mass balancing, and its purpose is to reduce control surface flutter. Flutter is a phenomenon associated with the higher speeds of aircraft. It is an oscillation of the control surface, coupled with an oscillation and bending or twisting of the wing, fin or tailplane. It can occur on aircraft with manual or powered flight controls. Flutter is likely to occur if the centre of gravity of the control surface is behind the hinge line. Uncontrolled flutter can cause structural failure. Flutter can be prevented by moving the centre of gravity of the control surface onto its hinge line by adding weights to the control. This reduces the inertia moments about the hinge line. This is known as mass balancing, and it can be applied to elevators, ailerons and the rudder. Common methods of mass balancing are shown in the picture. This picture shows the mass balancing of the aircraft's ailerons. That is the end of the lesson on aerodynamic balance. Remember that manually operated flight controls are known as reversible controls. Shown on the screen is a list of all the balance systems discussed in this lesson. You can click on a system to see a short summary of its purpose and operation. The secondary flight controls consist of lift augmentation devices, flaps and slats, lift dumping devices, spoilers, except when they are used for roll control, and air brakes and trimming controls. Some or all of these devices may be fitted to a particular aircraft. In this lesson, we will look at the operation of trailing edge flaps, leading edge flaps, and slats. The purpose of trailing edge flaps is to increase the lift generated by the wings at low speed. They are normally only used for takeoff and initial climb-out, and approach and landing. They produce a lot of drag, so it is important that they can be retracted when not required. There are various types of flap design which all increase both lift and drag in varying amounts. A full explanation of the aerodynamics of trailing edge flap operation is outside the scope of this lesson. However, here is a brief summary of the most common types. Click on a flap type to view its properties and operation. The most popular type for light aircraft is the plane or camber flap, with trailing edge flaps, which are a combination of slotted and Fowler flaps widely used on large transport aircraft. This picture shows the triple slotted Fowler flaps on the Boeing 747 in the fully extended landing position. In a typical system, there is a flight deck selector lever. On light aircraft, this is mechanically connected to the flaps. But on larger aircraft, it will either be mechanically or electrically linked to a flap control valve. The flap control valve controls the flow of hydraulic fluid to a flap drive unit, which consists of a hydraulic motor and a gearbox. The motor drives a transmission system, which moves the flaps. In the typical system shown here, the motor drives the gearbox, which rotates torque tubes. They operate right-angle gearboxes, which in turn drive screw jacks to move the flaps. If either the hydraulic supply or the normal control system should fail, then a backup system, using either an alternate hydraulic supply or an electrical motor to drive the main gearbox, can be used instead. The system is monitored and controlled by a control computer. This computer looks after trailing and leading edge flap sequencing, as well as monitoring the system for malfunctions. If the flaps operate asymmetrically, and by that we mean the flaps on one side move out further than the other, the control computer will instantly stop the movement by shutting off hydraulic fluid to the motor and either closing a bypass valve and hydraulically locking the flaps, or operating brakes on the drive shafts. Similarly, if the flaps move without the lever being moved, or they overshoot the selected position, then again the computer will shut off the hydraulic supply and lock the flaps. The computer also receives airspeed information. If a flap selection is made at an airspeed above the maximum permitted airspeed for the selection, then the computer will not allow the flap to operate until the speed is within limits. Similarly, if the aircraft is accelerated above the limit speed for the current flap position, then the computer will cause the flap to retract to a safe position. This is known as the Flap Load Relief System, or LRS. Wing leading edge devices may consist of slats, Kruger leading edge flaps, or variable camber leading edge flaps, or some combination of these. The Boeing 747, for instance, uses Kruger flaps on the inboard section of the wing leading edges and variable camber flaps for the outboard. while the Boeing 737 has inboard leading-edge Kruger flaps and outboard slats. Whenever a mix is used, the Kruger flaps will invariably be fitted closest to the wing root. Leading-edge flaps and slats are operated by hydraulic power or by air turbine motors, and are normally sequenced to operate with the trailing edge flaps. Leading edge flaps are hinge surfaces that extend by rotating downward from the lower surface of the wing leading edge. They only have two positions, retracted and extended. The Kruger and the variable camber flap look the same from the outside when they are retracted. Each is simply a flat panel on the bottom of the wing. When the Kruger flap extends, the panel maintains its flat shape. The variable camber flap, on the other hand, has a cam system which bends the panel into a curved aerofoil shape as it extends. The panel returns to its flat profile on retraction. Slats are sections of the wing leading edge that extend forward to an intermediate position to form a sealed leading edge. Or they can extend fully, forming a slotted leading edge, depending on the trailing edge flap setting. The leading edge flap or slat extension sequencing varies with aircraft type. On the Boeing 737, the leading edge flaps extend fully and slats extend to the midway position, when the trailing edge flaps extend to their first position. And when the trailing edge flaps are fully lowered, the slats extend fully. The sequence is reversed when the flaps are retracted. Whatever extension sequence is used, the leading edge flaps and slats will normally be retracted when the trailing edge flaps are retracted. Alternate operation of the leading edge devices may be by a standby hydraulic system, or, in the case of those powered by air turbine motors, an electrical standby system. Depending on the aircraft type, it may or may not be possible to retract the leading edge devices by the alternate system. Some aircraft types have an auto-slat system, which will automatically extend the slats from the intermediate position to the fully extend position if the aircraft approaches the stall angle of attack and the slats are not already fully extended. The trailing edge flap and leading edge flap or slat positions are displayed on the flight deck. On older aircraft, this may be a simple double pointer gauge, as shown here for the trailing edge flaps, with the leading edge flap and slat positions being indicated by coloured lights. On more modern aircraft, the positions may be displayed on an electronic screen. As you have seen previously, the electronic display is able to provide a lot of information. In this Airbus system, the selected flap position is shown on the indicator. When the flap lever is moved, the new selection is displayed in cyan. It will change to white when the flaps reach the selected position. And in the event of a fault, it will change colour to amber. That is the end of the flaps and slats lesson. Here are the main points from the lesson. Light aircraft usually use plain or camber trailing edge flaps, while large airliners use hydraulically operated slotted Fowler flaps. Leading edge flaps are hinge surfaces that extend by rotating downward from the lower surface of the wing leading edge. They only have two positions, retracted and extended. Variable camber flaps have a surface which bends, increasing its camber as it extends. Kruger leading edge flaps are usually placed inboard. Slats are sections of the wing leading edge that extend forward. They may have an intermediate setting, as well as being able to extend fully. The leading edge devices are normally operated either hydraulically or pneumatically. In this lesson, we will discuss the various methods used for trimming an aircraft in roll, pitch and yaw. An aeroplane is said to be in trim when it maintains its attitude and speed without the pilot having to apply any load to the cockpit controls. If the pilot does need to move a control surface to maintain the balance of the aircraft, he will need to apply a force to the cockpit control to hold the surface in its deflected position. This is commonly known as stick force, irrespective of which control is being operated. This force may be reduced to zero, thereby reducing pilot fatigue, by operation of the trim controls. The aircraft will need to be trimmed in pitch as a result of changes of speed, changes of power, or varying centre of gravity positions. Trimming in yaw will be needed on a multi-engine aircraft if there is asymmetric power, or on a single-engine aircraft as a result of changes in propeller torque. Trimming in roll is less likely to be needed, but could be required if there is asymmetric power or if there is a lateral displacement of the centre of gravity. There are 5 methods commonly employed to trim the aircraft. In this lesson, 4 of them will be explained. The 5th, adjustment of the artificial feel unit, is covered in the lesson on powered flying controls. The 4 we are going to discuss are the trimming tab, the variable incidence tailplane, the spring bias system, and centre of gravity adjustment. The trimming tab is a small adjustable surface set into the trailing edge of a main control surface. Its deflection is controlled by a trim wheel or switch in the cockpit, usually arranged to operate in an instinctive sense. This allows the aircraft to be maintained in trim throughout its entire operating envelope. Here, we will describe the operation of an adjustable trim tab fitted to the elevator control. However, the explanation remains good for a tab fitted in either the rudder or aileron systems. If the pilot were to pitch the aircraft nose up, then to continue to fly at that new attitude, a force must be continually applied to the controls by the pilot to balance the control surface hinge moment. The tab is moved in the opposite direction to the control surface to apply an increasing opposing hinge moment at the control surface until its hinge moment balances the control surface hinge moment. You will recall from the aerodynamics lessons that the hinge moment is equal to the aerodynamic force, multiplied by its distance from the hinge line. In this example, the control surface hinge moment is distance A multiplied by force F2. Although the tab is small in relation to the control surface, and its aerodynamic force F1 is similarly small, its distance B from the control surface hinge line is much greater than that of the control surface force distance A, so it is able to balance the control surface hinge moment. The aircraft will be in trim when F2 multiplied by distance A equals F1 multiplied by distance B. There are a number of disadvantages to using an adjustable tab type control to achieve trim. These are a slight reduction in control effectiveness due to the tab force being in opposition to the main flying control surface, and an increase in drag due to the deflection of the tab. Fixed trim tabs are not adjustable in flight, but can be adjusted on the ground to correct a permanent out-of-trim condition. They are usually found on ailerons. They operate in the same manner as the adjustable tabs. Fixed tabs are used on simple low-performance aircraft. They achieve an in-trim condition at a particular speed, normally the aircraft's cruising speed. Their correct position is usually found by a process of trial and error. A variable incidence trimming tailplane or stabilizer does not have the disadvantages of the adjustable elevator trim tab. Plus, it has the ability to trim for larger changes in speed and centre of gravity position. The system is controlled from the cockpit and can be either manual or power operated. The operating power may be electrical or hydraulic. The Boeing 737 stabilizer trim, for instance, is electrically powered, whereas the one on the 747 is hydraulically operated. In a power-operated system, tailplane movement can be controlled either manually or electrically. Electrical control is by trim switches, which operate in pairs. These are usually found on the control column or yoke. There may also be a pair of manual control levers mounted on the centre console. Either both switches or both levers must be moved simultaneously in order to trim the aircraft. And as a pilot, this is how you always use them. Consider them to be a single switch or lever. The reason why there are two switches and two levers is to prevent the short-circuiting of a single switch or the jamming of a single lever, causing an undemanded trim operation or trim runaway. An example of the operation of a variable incidence trimming tailplane to achieve trim after a change of attitude is shown in this graphic. The elevator is deflected to change the pitch attitude. The angle of incidence of the tailplane is now altered by the pilot to achieve trim. The amount of trim required will depend on the centre of gravity position. In order to ensure that the aircraft will be trimmed in pitch on takeoff, recommended takeoff stabilizer settings based on aircraft weight and centre of gravity position will be given in the aircraft flight manual. The acceptable takeoff range for the stabilizer setting will normally be shown on the stabilizer trim indicator by a green band. The stabilizer trim takeoff setting is one of the parameters monitored by the takeoff configuration warning system. This is a system that warns the crew if a takeoff is attempted with the critical system not correctly configured. The warning normally takes the form of an intermittent horn. The horn will sound if the aircraft is on the ground and the thrust levers are advanced for takeoff, and the stabilizer trim is not in the takeoff range, or the trailing edge flaps are not in the takeoff position, or the leading edge devices are not in their takeoff positions, or the speed brake lever is not in the down position. This list does vary slightly between aircraft types. Some aircraft systems also monitor other items, such as the parking brake, external doors, body gear steering, or even control locks. In the spring bias type of trim system, an adjustable spring is used to reduce the stick force. No tabs are required, so the spring system does not have the disadvantages associated with tabs. The spring bias system differs from the other systems discussed so far, in that the device is connected not to the flying control surface, but to the pilot's control. The trim control biases springs which apply a force to the control linkage to oppose the stick force. The graphic shown here demonstrates the use of spring bias in a rudder control system. The pilot operates the rudder pedals to move the rudder. He will now have to maintain a force on the pedals to oppose the rudder hinge moment. By rotating the rudder trim knob, the angle of the arm between the springs is changed, thus biasing the spring pressures until they are equal to the hinge moment. The pilot can now remove his feet and the rudder will remain in position. We will now look at longitudinal trim by centre of gravity or C of G adjustment. While the variable incidence tailplane produces a drag reduction over a trimming tab, the minimum drag will be produced if the tailplane can be made aerodynamically neutral. This can be achieved by moving the aircraft's centre of gravity as close as possible to the wing's centre of pressure. On long-haul aircraft, this can produce a significant fuel saving. The method usually employed to move the centre of gravity is by transferring fuel between tanks located at the nose and/or tail of the aircraft. The Airbus A340, for instance, has a fuel tank in the tail specifically for this purpose. Fuel is automatically transferred between this and the wing tanks to maintain the C of G as close to the centre of pressure as possible. In the graphic shown here, the C of G is forward of the centre of pressure. Fuel is pumped from the forward to the aft tank, moving the C of G aft until it reaches the centre of pressure, when the pumping stops. On most large turbojet aircraft, the wing centre of pressure moves rearward as the aircraft approaches high subsonic speed, and this produces large nose-down pitching moments, known as tuck-under or mac-tuck. It is essential that the aircraft is fitted with an automatic system to correct this change in pitch attitude. Such a system is known as Mac trim, and is designed so that it will operate whether or not the autopilot or some other method of automatic flight control is engaged. The system senses speed increases above a datum Mach number, approximately Mach 0.65, but this does vary with aircraft type, and through a servo system produces the appropriate movement of the horizontal stabilizer, or a fuel transfer to maintain the trim flight position. The trim controls are usually on the centre pedestal. In this typical setup, there is a large wheel for pitch trim, a smaller wheel for rudder trim, and a guarded switch for aileron trim. You will note that the wheels and switch all operate in the plane in which they trim. If the pitch trim can be controlled electrically, then there will also be control switches on the outboard arm of each yoke or control wheel. That is the end of the lesson on trimming. These are the main points that you need to remember. The trimming tab is a small adjustable surface set into the trailing edge of a main control surface. It allows the aircraft to be maintained in trim throughout its entire operating envelope, reducing the stick holding force to 0. Fixed trimming tabs are not adjustable in flight. They can only be adjusted on the ground. The disadvantages of trimming tabs are a slight reduction in control effectiveness due to the tab force being in opposition to the main control flying surface, and an increase in drag due to the deflection of the tab. A variable incidence trimming tailplane does not have the disadvantages of the elevator trim tab. Plus, it has the ability to trim for larger changes in speed and centre of gravity position. It is controlled by 2 switches or levers to reduce the possibility of trim runaway. Longitudinal trim by centre of gravity adjustment is used to maintain the centre of gravity close to the wing centre of pressure. It is normally achieved by transferring fuel between forward and aft tanks. MAC trim is an automatic system used to counteract MAC tuck at high subsonic Mach numbers. In this lesson, we will discuss the aerodynamic devices that are used to reduce lift and/or to slow the aircraft down. A spoiler is a device intended to reduce lift in an aircraft. Spoilers are flat panels on the top surface of a wing, which can be extended upward into the airflow and spoil it. By doing so, the spoiler creates a carefully controlled stall over the portion of the wing behind it, greatly reducing the lift of that wing section. Air brakes are designed to increase drag, while making little or no change to lift, while spoilers greatly reduce lift, while making only a moderate increase in drag. However, most aircraft only have spoilers. They form part of a speed brake system which can be used to slow the aircraft down in flight and on the ground. When operated, they reduce the lift on the wing. Thus, in order to maintain altitude, the aircraft has to be pitched up, increasing drag and reducing airspeed. We will have a look here at a typical aircraft speed brake system, using spoiler panels on the upper surface of the wings. There are a number of panels on each wing. The Boeing 737, for instance, has 6 on each wing. The panels are hinged at their forward edge and are extended into the airflow by individual hydraulic actuators. They are split into 2 groups. One group is known as the ground spoilers, and the other the flight spoilers. The ground spoilers operate exactly as suggested by their name. They only operate when the aircraft is on the ground. They are inhibited in flight, normally because they produce undesirable aerodynamic effects. They always operate symmetrically. The flight spoilers are slightly more complicated. They operate both in flight and on the ground. They are used both as symmetrical spoilers for slowing down or descending the aircraft, and they are also used asymmetrically for roll assistance. This function is fully explained in the primary flight controls lesson. The pilot controls the spoilers by a speed brake lever adjacent to the thrust levers. Speed brake lever inputs produce symmetrical spoiler operations. Operating the lever on the ground will extend all the spoilers. In flight, only the flight spoilers will be deployed. The speed brake lever typically has a number of detents marked on it. With the lever in the down detent, all flight and ground spoilers are retracted. The flight spoilers are, however, available for roll assist. This applies both on the ground and in flight. To move the lever from down to the arm position, it has to be raised up out of a gate. The arm position is selected on approach. With the lever in this position, the automatic speed brake system is armed. When the aircraft touches down and certain parameters are met, the lever will move automatically to the up position, and all panels, both flight and ground spoilers, will fully extend. We will discuss this system fully later in the lesson. In flight, the speed brake lever is not able to move beyond the flight detent. The detent limits the flight spoilers to approximately 2/3 of their maximum, leaving some movement available for roll assistance. The up position is only used on the ground. With the lever in this position, all spoiler panels, both ground and flight, are fully extended. Shown here is a typical spoiler control setup. To provide redundancy, 2 of the flight spoilers on each wing are powered by one hydraulic system, with the other 2 being supplied by a different system. There are hydraulic shutoff valves in the lines to the flight spoilers, controlled by flight deck operated shutoff switches. There is a ground spoiler shutoff valve which is open when the aircraft weight is on the wheels and closed when it is not, thus ensuring that the ground spoilers operate only on the ground. There is also a ground spoiler control valve which is under the control of the spoiler mixer. This valve will open and close to control the position of the ground spoilers in response to speed brake lever movement, only of course on the ground. The closed in-flight ground spoiler shutoff valve preventing their operation whilst airborne. The spoiler mixer receives inputs from the speed brake lever and the yoke in roll. It sums these inputs before signalling the flight spoilers to move the required amount. If in flight the speed brake lever is operated with no roll input, then the flight spoilers will raise symmetrically in proportion to the amount of lever movement. If a roll input is made with the speed brake lever in the down detent, then the flight spoilers on the downgoing wing will raise in proportion to the roll input. Those on the upgoing wing will remain retracted. Finally, if a roll input is made with the speed brake lever out of the down detent, then the flight spoilers on the downgoing wing will raise further, while those on the upgoing wing will retract by a similar amount. Most spoiler systems have a blow-back facility, whereby if the spoiler panels are raised at high speed, the air load will overcome the hydraulic jacks and push the panels down. This is progressive with increasing airspeed until eventually the panels are blown down to the fully retracted position. This applies when the panels are being operated by the speed brake lever or by the roll assist mechanism, the latter reducing the sensitivity of the aircraft in roll with increasing speed. During the landing run, the decelerating force is produced by aerodynamic drag and the drag of the wheel brakes. The wheel brake drag depends on the weight on the wheels. This is reduced by any lift that the wing is producing. The wing lift can be reduced by operating the spoilers. Both the brake drag and the aerodynamic drag will be increased, and the landing run reduced. As we have already said, on many aircraft types, additional spoilers are provided for use on the ground. The ground spoilers are made inoperative in flight by a switch on the undercarriage leg, which is operated by the extension of the leg after takeoff. If the speed brake lever is moved to the up position on the ground, then all spoiler panels, both flight and ground, will extend fully, giving the required wing lift dump and drag increase. Many aircraft have an electrical actuator connected to the speed brake lever, which, when certain parameters are met, will automatically drive the lever to the up position and deploy the spoilers. Prior to landing, the pilot must place the speed brake lever in the arm detent. This arms the automatic ground speed brake system. Once the lever is armed and an on-ground signal is received, the actuator will drive the lever to the up position. In order to prevent spurious operation, 2 or more different on-ground signals are usually required to operate the actuator. Different aircraft types use various different parameters. They will usually include 2 or more of the following: the radio altimeter reading less than 10 feet, the wheel brake anti-skid system sensing wheels spin up, the air-ground sensing system giving an on-ground signal, and the thrust levers being fully closed. If the speed brake lever is in the down detent, which is where it would be for takeoff, and the engine thrust reversers are operated, then a mechanical linkage will raise the speed brake lever to the arm position. Provided the aircraft is on the ground, the electrical actuator will drive the lever to up, and all spoiler panels will deploy. This gives automatic ground speed brake operation in the case of a rejected takeoff, or RTO. The system will have a go-around capability, whereby if after touchdown and spoiler deployment, the pilot decides that for some reason his safest course of action is to get airborne again, then if the thrust levers are opened, the speed brake lever will be driven to the down position, and the spoiler panels will retract. The electrical actuator can be overridden at any time by the pilot operating the speed brake lever. A small number of commercial aircraft have fuselage-mounted air brakes fitted. This type of air brake produces an increase in drag, with little or no loss of lift or change in pitching moment. An example is seen here on the rear fuselage of the British Aerospace 146. That is the end of the lesson. You should now understand the difference between spoilers and air brakes. Remember that ground spoilers operate only on the ground, while flight spoilers operate both in flight and on the ground. Bear in mind that when the speed brake lever is operated, the spoilers respond symmetrically. But when used for roll assist, they operate asymmetrically, the spoiler on the downgoing wing extending, and the one on the upgoing wing retracting. In this lesson, we will discuss manual operation of the primary flight controls. The movement of the flying control surfaces, in response to the movement of the cockpit controls, may be achieved manually on smaller aircraft. In a manual system, the control surfaces are connected directly to the cockpit controls by a system of cables, rods, levers and chains. Most manual control systems use flexible wire cables to transmit the movement from the pilot's control to the control surface. Cables have a number of advantages over push-pull rod type linkages. They have a very good strength-to-weight ratio. They are easy to route through the aircraft. Their direction can be easily changed using pulleys. Because of their flexibility, they are resistant to impact damage, and they take up less room and have less joints than systems using solid rods. In this graphic, we examine the manual control of the elevator on a light aircraft. The control of the rudder and ailerons is achieved in a similar manner using similar components. As cables can only operate in tension, the control surface is connected to the input control by 2 cables. The system is very simple in its operation. The pilot operates his control. It is connected by a push-pull rod to a lever arm which drives the cables. They in turn rotate another lever arm at the flight control end of the system. This moves another push-pull rod, which operates the flight control. Pulley wheels are used where direction changes are required. In order to move the control, the pilot has to overcome the aerodynamic load or stick force. If he releases the control, this force will drive the control surface and the control back to neutral. Manual flight controls are therefore known as reversible controls. You will see in another lesson that powered flying controls are irreversible or non-reversible. The amount of movement of the control surface to either side of its neutral position is laid down, so that the required control can be achieved over the full range of operating conditions. The movement is not necessarily the same each side of neutral. For example, an elevator may have more control deflection upwards than downwards. The limit of movement of the control surface is determined by a mechanical stop. The function of mechanical stops is to prevent excessive control surface deflection, which may cause the aircraft structure to be overstressed during normal operations. The stop which limits the movement of the control surface is called a primary stop. A stop which limits the movement of the control column or rudder pedals is known as a secondary stop. When the control surface reaches the primary stop, there will be a small clearance at the secondary stop. If the pilot should apply excessive force to the controls, the secondary stops will prevent him from damaging the control linkages. A fair lead is a guide, manufactured from a soft metal or plastic, used where the control cable passes through the airframe structure, so that if the cable were to flex laterally, it would come into contact with the fair lead rather than the airframe structure. It is important to have the correct tension in the control cables. If the tension is too low, the cables will be loose, permitting excessive cable movement. And if the tension is too high, the controls will be too stiff to move. Cable tension is adjusted by means of turnbuckles. Here we show a typical turnbuckle. It consists of a central barrel and two end fittings screwed into the barrel, one with a right-hand thread and the other with a left-hand thread. The cable is attached to the end fittings. The cable tension is adjusted by rotating the central barrel, causing the end fittings to screw either into or out of it. Sufficient screw thread must be engaged between the end fittings and the central barrel of the turnbuckle to take the load which will be placed on the cable. To enable this to be checked, inspection holes are provided in the turnbuckle. To be in a safe condition, or in safety, the inspection holes must be completely blocked by the threads of the end fittings. This is verified by attempting to pass a hardened pin through the inspection hole. Once the correct tension is set, the turnbuckle is locked using locking wire or some other suitable device to prevent it vibrating loose. Changes of temperature will change the length of the cables and also the dimensions of the airframe structure, but as they are made of different materials, the rate of expansion will be different. This will cause a change in cable tension. On some aircraft, a temperature compensator is fitted in the control system. This automatically maintains the correct tension if the temperature changes. In the temperature compensator in this graphic, the cables from the pilot's control are fastened to the two quadrants. The quadrants are free to rotate independently about the central pivot point. However, they are connected together by a strong spring in the damper unit. Movement of the pilot's control operates the cables. They rotate the quadrants equally, moving the push-pull rod and the control surface. If there is an increase in cable tension due to temperature change, then the cable tension will overcome the spring and rotate both quadrants as shown, reducing the tension back to the correct level. Similarly, if the tension reduces below the correct level, then the springs will push the quadrants in the opposite direction, again correcting the tension. Control systems should be free of backlash. Backlash is free or ineffective movement of the cockpit control when the direction of movement is reversed. It may indicate worn or incorrectly adjusted components in the control system. Excessive backlash can exacerbate the problem of control surface flutter. As you can see in the extreme example shown here, the column has to be moved a considerable distance before there is any reaction from the flight control surface. When an aircraft is parked in the open, strong or gusty winds could blow the controls against their stops with sufficient force to cause mechanical damage. To prevent this occurring, control locks are fitted. These may be external or internal, and may be fitted to the control surface or to the cockpit control. If they are fitted to the cockpit control, they may be arranged so that it is impossible to open the throttle until the control locks are removed. External locks have high visibility flags fitted. Obviously, all locks must be removed before flight. That is the end of the lesson on manually operated flying controls. You now know the advantages that cable control has over other systems. You should understand the purpose and function of the mechanical stops, pulley wheels, and fair leads. You should also understand what is meant when we describe a manual system as being reversible. Finally, you should understand the purpose of turnbuckles and temperature compensators. As aircraft have become larger and faster, the increasing air loads have made it impossible for the pilot alone to have sufficient strength to comfortably control the aircraft. The maximum permissible loads that the pilot needs to overcome to operate the controls are specified in EASA regulations. They are, of course, subject to amendment, but just to give you an idea, at the time of writing, the maximum continuous stick forces allowed were 10 pounds in pitch, 5 pounds in roll, and 20 pounds in yaw. You will see in another lesson that various aerodynamic devices can be used to assist the pilot. However, there comes a point where some form of power assistance is required. Power-assisted flying controls have hydraulic actuators assisting the pilot, while in fully powered systems, the entire load is taken by hydraulic actuators. A simple power-operated flying control system consists of 4 essential parts. They are a hydraulic actuator to move the control surface, a servo or control valve to control the actuator, a follow-up or feedback system to ensure that the actuator movement stops when the required displacement is achieved, and for a fully powered system, an artificial feel unit, as the pilot will not receive any aerodynamic feedback. Illustrated here is a schematic diagram of a hydraulic power-assisted flying control unit. It consists of a hydraulic actuator or jack with a servo unit mounted on its body. The hydraulic actuator differs from those we have seen before in that the actuator body is not fixed, but is connected to the flight control linkage, and it is the actuator body which moves to hydraulically operate the flying control, while the ram is connected to the pilot's control column. There is a second connection to the pilot's control. This connection moves the valve in the servo unit. With the system in the situation shown here, that is, with the control column central and the flight control in its neutral position, the servo valve will be in a central position, blocking off both the hydraulic pressure and return from the actuator, producing a hydraulic lock across the piston. We will first look at how the system will operate without hydraulic power. When the pilot makes a control input, he will be attempting to move the hydraulic jack ram. Because of the hydraulic lock, the entire actuator will move, and with it the flying control. However, because of the mechanical advantage gained, the control surface movement will be small compared to the pilot's input. There will normally be sufficient movement available for the pilot to maintain control of the aircraft in the event of a hydraulic system failure. We will now look at the operation of the system with hydraulic power available. Once again, when the pilot operates his control, the hydraulic lock will cause the actuator body to move, and with it the flying control. Because of the position of its connection on the control column, the servo valve will move further than the jack body. So one port of the actuator will open to hydraulic pressure, and the other will be open to return. The hydraulic pressure will attempt to move the actuator ram. This movement will be opposed by the pilot, so instead the body will move in the opposite direction, moving the flying control. As the actuator housing moves, it gradually repositions the actuator ports in relation to the servo valve pistons until the fluid is shut off and movement stops. Control surface movement is therefore amplified in proportion to the pilot's control input. In this system, the pilot is still feeling the aerodynamic loads on the control surface and must hold the control in position to oppose them. If the pilot releases the control, these loads will return his control to the centre and bring the control surface back to neutral. Power-assisted flying controls are therefore reversible controls in the same way as those in a manual system. In a fully powered flying control system, all of the work in operating the flying control is done hydraulically. There is no direct connection between the pilot's input and the flying control surface. The system components are very similar to those used in the power-assisted system. The Powered Flying Control Unit, or PFCU, is the same, except that in this case the actuator ram is bolted to the aircraft structure. This means that the ram cannot move. The pilot's control only operates the servo valve. In our example here, the pilot pushes the control column forward. When the column is pushed forward, the servo valve is moved over to the right by the control linkage. This action opens the right-hand port of the actuator to hydraulic pressure, while opening the left-hand port to return. Since the ram is fixed to the aircraft, hydraulic pressure will now move the actuator housing over to the right, thus lowering the elevator. As the actuator housing moves, it gradually repositions the control valve pistons until they cover the actuator ports again, thereby cutting off further hydraulic supply and blocking off the return port. This creates a hydraulic lock in the actuator and prevents further control surface movement. This is a non-reversible system, in that the aerodynamic loads on the control surface cannot move it or the control column. The control surface is held in the last selected position by the hydraulic lock. When the flying controls are power operated, some form of control unit duplication is necessary to guard against hydraulic system failure. This is often accomplished by having two powered flying control units operating each flying control surface. These units will be operated by separate hydraulic systems. Each powered flying control unit has a bypass piston fitted, which is normally held closed by hydraulic pressure. Should a hydraulic system fail or be taken offline by the pilot, then the drop in hydraulic pressure will allow the spring-loaded piston to open the bypass channel and so break the hydraulic lock in the actuator. This will permit the fluid to flow from one side of the piston to the other, allowing the powered flying control unit to follow the control movement of the other unit. That is the end of the lesson. You have learned that powered flying controls are operated hydraulically, that power-assisted systems are reversible, and fully power-operated systems are non-reversible. You have also seen that powered flying control units are usually duplicated, with each unit being powered by a separate hydraulic system. In this lesson, we will examine the artificial feel systems used by powered flying controls, and then we will look at some of the safety and backup systems built into powered flying control systems. When fully powered flying controls are operated, there is no aerodynamic stick force fed back to the pilot. He therefore has no feel for the aerodynamic effect his control movements are having, meaning that there is a danger of him over-controlling the aircraft or of overstressing the airframe. To prevent this problem, and to ensure that the control centre when the pilot's control input is removed, artificial feel units are fitted in parallel with the powered flying control units, or PFCUs. The simplest feel unit consists of a box containing two springs, known as a spring box. Movement of the control column in either direction will compress one of the two springs. While this will give the pilot feel and will centre the controls when the control input is removed, the feel will not be proportional to the air loads. It will be the same over the entire speed range. Most modern aircraft have feel units fitted with devices known as Q-pots. These devices measure dynamic pressure in the same way that an airspeed indicator does. Q is the commonly used abbreviation for dynamic pressure. In the system shown here, static air pressure is felt on one side of a piston, with pitot pressure on the other. The piston, therefore, is feeling the difference between pitot and static pressure. The force pushing the piston to the right will therefore be proportional to airspeed, and thus proportional to the aerodynamic force being felt at the control surface. When the pilot makes a control input in either direction, the bell crank linkage to the Q-pot means that he has to overcome the dynamic pressure in order to operate the PFCU. Whilst the feel produced by a Q-pot is proportionally correct, its magnitude is quite small. To produce feel of a significant magnitude, the Q-pot would have to be very large. So Q-pots are normally used to control hydraulic pressure, which is used to amplify the feel up to a usable level. In the schematic shown here, the Q-pot controls the position of a hydraulic spool valve. The pressure gauge is not part of the system. It is shown only for illustrative purposes. The pilot's flight control input is connected to a hydraulic piston, he has to overcome the hydraulic pressure being applied to the piston in order to operate the control. With the forward movement of the aircraft, pitot pressure is fed to the upper chamber of the Q-pot section of the unit, pushing down the diaphragm. The diaphragm is connected to a spool-type selector valve, so that the downward movement of the diaphragm opens the hydraulic pressure port and partially closes off the return port. Hydraulic fluid emitted to the unit will then pass to the forward side of the piston. The fluid also passes through a narrow channel to the underside of the spool valve to dampen its downward movement. As the airspeed increases, the pitot pressure will increase, pushing down on the diaphragm, increasing the size of the opening of the pressure port in the selector, which means that the pressure in front of the piston will increase, thereby increasing the resistance to control movement. The return port is never fully closed, as this would cause a hydraulic lock to form in the system. The Q-pot artificial feel system gives increased feel with increasing airspeed. However, when the aircraft is stationary or moving slowly, it produces very little feel or control centering. Some systems combine the spring box and Q-feel systems. The spring produces the majority of the feel and centering when the speed is low. In the system shown here, the spring and the hydraulic piston both operate against a cam. This increases the feel effect with increasing control input deflection and produces a positive centering force at all speeds. Having artificially produced the feel, there are going to be times when the control needs to be other than central. The rudder, for instance, will need to be held displaced in the event of engine failure on a multi-engine aircraft, or the yoke will have to be held back in a climb. Each of the three primary controls has a feel trim system which allows the feel to be reset to 0 with the control away from neutral. Shown here is a rudder feel and trim unit. When the pilot makes a rudder input, the cam compresses the spring, thus providing feel. In the event of an engine failure, the pilot will have to hold the rudder away from the centre, and this will be opposed by the spring pressure. In order to relieve the load, he rotates the trim wheel. This will move the spring around its hinge point until it is acting through the centre of the cam, allowing the pilot to fly feet off. Safeguards to eliminate the possibility of loss of control in the event of hydraulic or mechanical failure must be provided on modern transport aircraft. This is generally achieved by building redundancy into the control system. Mechanical failure in the form of a jam in the control run is safeguarded against by having two sets of control cables running to the PFCU, one set controlled by the captain and the other by the first officer. The control columns are linked together so that movement of either control normally operates both cable runs together. In the event of a jam in either system, the coupling device can be opened either by pulling a handle in the cockpit or by applying excessive force to the controls. This will allow the pilot with the free control run to operate the flying control. Having more than one actuator, each of which is powered by a different hydraulic system, will allow the flight controls to be operated in the event of hydraulic failure. In this lesson, you have seen that fully powered flight control systems require an artificial feel system fitted in parallel with the controls, and that this is normally supplied by a hydraulically powered Q-pot. You also now know that both mechanical and hydraulic redundancy is built into the fully powered flying control systems of all large airliners. In this lesson, we will examine the fly-by-wire flight control systems, in use on many of the most modern large aircraft. Mechanical and hydromechanical flight control systems are heavy and require careful routing of flight control cables through the aircraft, using a system of pulleys and cranks. They also require a lot of maintenance, in the form of lubrication, tension adjustments, and so forth. These systems have a very limited ability to prevent dangerous characteristics, such as stalling or spinning. Electronically controlled flight controls, in systems known as fly-by-wire systems, overcome many of these problems. By using electrical control circuits combined with computers, designers can save weight, improve reliability, and use the computers to prevent undesirable aerodynamic characteristics. Between the pilot and the final control actuator, a computer system is interposed. This modifies the pilot's inputs in accordance with carefully developed and validated software programs, in order to produce maximum operational effect without compromising safety. The pilot's commands are converted to electronic signals. These signals are passed to the flight control computers, which determine how best to move the actuators at each control surface to provide the desired response. The actuators are still usually hydraulically operated. The computer monitors the aircraft's response to the flight control movement and modifies its output to the powered flight control unit as required. All Airbus aircraft since the A320 series have used fly-by-wire controls. Boeing have followed with their 777 and later designs. Side sticks, or conventional control yokes or wheels, are used in fly-by-wire aircraft. The side stick offers the advantages of being lighter, mechanically simpler, and unobtrusive. Standard rudder pedals are used. Boeing consider the lack of visual feedback from the side stick a problem, and so use conventional yokes in their fly-by-wire designs. The Airbus series have used side sticks extensively, and the new Airbus A380 uses them. The main concern with fly-by-wire systems is reliability. While traditional mechanical or hydraulic control systems usually fail gradually, the loss of a flight control computer could immediately render the aircraft uncontrollable. For this reason, fly-by-wire systems incorporate either multiple redundant computers, some kind of mechanical or hydraulic backup, or a combination of both. The Airbus A320 fly-by-wire system is a fairly typical system, so we will now take a look at its features. There are 7 computers and 3 hydraulic systems looking after the primary flight controls. Each primary flight control has 2 hydraulic actuators, each fed from one of 3 independent hydraulic systems. There are 2 elevator aileron computers, or ELACs. These control the elevators, ailerons, and stabilizer. Only one of these computers is controlling at any time. The other is a backup and will automatically take over in the case of a failure. There are 3 spoiler elevator computers, SECs. They control the spoilers. And in the event of failure of both elevator aileron computers, they will also control the elevators and stabilizer. Although the pilot controls the rudder through a conventional hydromechanical system, there are also 2 flight augmentation computers, FACs, which operate the rudder to automatically give roll assistance. The stabilizer trim is hydraulically operated. It can be mechanically controlled by the pilot's trim control wheel. This system has both electrical and hydraulic redundancy built into it. The elevator and ailerons have access to up to 5 computers, only one of which is needed for them to operate. The aircraft has 3 hydraulic systems. Each control surface can be operated by either one or 2 of these systems. Even if 2 of the hydraulic systems fail, the aircraft will still be controllable. In the event of a total electrical failure, the aircraft can be controlled longitudinally with the trim wheel and laterally with the rudder pedals, both of which operate their control surfaces hydromechanically. To summarize fly-by-wire systems, they are lighter than conventional systems, and they improve the control of the aircraft throughout the flight envelope. As with conventional systems, they have a great deal of redundancy built into them. In this lesson, we will discuss the various sources of air available to an aircraft's pneumatic system. We will also look at some basic cabin heating systems. Most aircraft have a pneumatic system of some sort. Large modern airliners have a high-volume, low-pressure system, supplying a bleed air manifold with air from the engine compressors. These systems are covered in a separate lesson. Light aircraft may use ram air, a dynamic air pressure created by the aircraft's motion, to operate gyroscopic instruments. They can also use ram air heated by the engine exhaust gases or by a combustion heater to heat the cockpit and cabin and to demist the windscreen. On some aircraft, where air from the engine compressor is not available, such as on large pressurized piston engine aircraft and some turbopropeller types, blowers driven by the engine are used to supply air to the air conditioning and pressurization systems. Some older turboprop aircraft use high-pressure pneumatic systems to operate the landing gear and brakes. The only example of this still in common use is in the Fokker F-27. The operation of this type of pneumatic system is covered in the hydraulic series of lessons. First, we will look at the ram air systems used in light aircraft. Outside air is introduced to the cabin through forward-facing air intakes. Some of this ram air can be heated by an exhaust gas heater or a combustion heater, and then mixed with the cold ambient air in varying proportions to give a comfortable cabin temperature. A typical system for a light aircraft using an exhaust gas heater is shown here. It also features hot windscreen demisters and a fresh air blower for use on the ground when there is no ram air. The heater muff or exhaust muff is a close-fitting cowl around the exhaust pipe, which allows ram air to come into close contact with the hot exhaust pipe to provide hot air for heating the cabin and demisting the windscreen. Fresh, cold air is allowed into the cabin through the ram air inlets on the wing leading edge. After use, the air is dumped overboard through a vent on the underside of the aircraft. This type of heater requires regular inspections to ensure that toxic exhaust gases do not enter the manned areas. Some aircraft have a blower which can be used on the ground to blow fresh air into the cabin, giving some cooling on hot days. Some aircraft use a combustion heater rather than an exhaust gas heater. The combustion heater is a standalone device. It normally uses the same fuel as the aircraft's engines. It burns about half a gallon an hour. This needs to be taken into account when calculating the fuel required for a particular flight. It works by burning a fuel-air mixture within its combustion chamber. Air for combustion is supplied by a fan or blower known as the combustion blower, and the fuel is supplied via a solenoid-operated fuel valve. The flame is lit by an ignition unit controlling an igniter. The fuel valve and the igniter are controlled by duct temperature sensors, but can be manually overridden. The system is designed with the fan pushing the air into the cabin being much more powerful than the combustion blower fan. This means that the clean air is at a higher pressure than that in the combustion chamber, so there is no possibility of leaks from inside the chamber contaminating the cabin air. The combustion heater is provided with a number of safety devices, which will include an automatic shut-off if the outlet air temperature becomes too hot, and adequate fire protection in the event of failure of the structural integrity of the combustion chamber. This will normally be a system for shutting off the fuel and sealing the air ducts if flames enter them. An automatically operated fire extinguisher is also incorporated in some systems. A cabin air supply may be provided by blowers driven through the engine accessory gearbox, or by turbo compressors driven by bleed air. Such systems are necessary for piston-engined aircraft and are used for some turbojet aircraft, where the air supply from the compressor is considered to be too dirty or contaminated for use in the air conditioning system. These blowers operate in a similar manner to the superchargers fitted to some piston engines. They may either have a centrifugal or a positive displacement type blower fitted. One type of positive displacement blower is known as the Roots blower. It is named after the Roots brothers, who first patented the basic design in 1860. It consists of two lobes which mesh together and are rotated by the engine gearbox. Air is pulled in through the inlet and expelled through the outlet. The pressure increase across the blower is small. However, this type of blower can produce large flow rates. Shown here is a simple schematic diagram of a cabin conditioning system using a Roots blower. Because of the design of the blower, the air comes out of it in short pulses. This can cause a thumping noise in the air conditioning ducts. The silencer helps to smooth out the airflow, reducing the noise. The blower must be capable of supplying the required mass flow of air under all operating conditions, which means that at high engine speed and low altitude, too much air is supplied. A mass flow controller signals a spill valve to vent the excess airflow to atmosphere. The air can be heated by restricting the flow by means of a variable restrictor, known as a choke valve, which can be progressively closed to increase the pressure and thus the temperature of the air leaving the blower. The hot and cold air supplies are mixed in varying proportions to maintain the delivery temperature at a comfortable level for both passengers and crew. Selection and control may be automatic or manual. The operation of the pack valve, hot air bypass valve, cooling pack and water separator is explained in the air conditioning lesson. In this lesson, you should have learned that most aircraft have a pneumatic system of some sort. On light aircraft, it usually consists simply of ram air, heated by either the exhaust gases or by a combustion heater, being used to warm the cabin. On larger aircraft, where the air is required to supply a pressurization system, it may be supplied by a cabin supercharger, or engine bleed air may be used. In this lesson, we will discuss the high-volume low-pressure air systems used by modern jet airliners. The system is normally supplied with bleed air from the engine compressors. This can be backed up with air from the auxiliary power unit, APU, and on the ground by external air supply carts. This air is used for air conditioning and pressurization, ice protection, and as a power source for the air turbine motors used for engine starting, driving hydraulic pumps, and air-driven flaps and slats. It is also used for pressurizing hydraulic reservoirs and potable water tanks, and for cargo compartment heating. The engine bleed air system consists of the power source, the engine compressor, and control devices for temperature and pressure regulation during operation. Because of the great variation of air output pressure from a gas turbine engine between idle and maximum RPM, there is a need to maintain a reasonable supply of air during low RPM, as well as restricting excessive pressure when the engine is at high RPM. This is usually done by taking air from two compressor stages to maintain a reasonable pressure band at all engine speeds. Here we show a typical bleed air system. Low pressure, LP air, is taken from an early compressor stage, and high pressure, HP air, is taken from a later stage. The high pressure source is controlled by the high pressure shutoff valve, HPSOV. This valve is pressure sensitive and pneumatically operated. It is open when there is insufficient air pressure from the LP system to maintain the required flow. When this valve is open, HP pressure will close the non-return valve, NRV, shutting off the LP supply. As the engine speeds up, the LP air pressure will increase until it closes the high pressure shutoff valve, so that, in most stages of flight, bleed air will come from the LP stage. The air from the compressor is too hot for its required purpose, so it is passed through a pre-cooler in order to reduce its temperature. This usually takes the form of a cooling matrix, with engine fan air being used as the cooling medium. The control valve modulates to vary the amount of fan air passing through the cooler, and thus control the temperature of the bleed air at a predetermined level, usually about 175 degrees Celsius. The engine bleed air control valves control the flow of bleed air into the pneumatic system manifold. They are controlled electrically by switches on the flight deck. When selected open, the bleed air valve acts as a pressure regulator. The valve position is automatically modulated to maintain a maximum duct pressure of approximately 55 pounds per square inch. If the output pressure is below this, the valve will be fully open. Some aircraft have separate bleed air and pressure regulating valves. However, they function in the same manner as the combined valve. It is a regulatory requirement that any single component in an aircraft's cabin air conditioning or pressurization systems, the failure of which could jeopardize the safety of the aircraft or the people in it, must be duplicated. To this end, most multi-engined aircraft keep the supplying engines or sides separate, with each engine supplying its own user services. These are kept independent by isolation valves, which are normally closed, but which may be opened if an engine supply is lost, to feed the other side services. The system is fitted with a two-pointer duct pressure gauge. One pointer displays the pressure in the left duct, and the other the right. Some systems have engine bleed air valve position indicators. However, in the system shown here, the valve position is shown by the switch position, unless a warning light is indicating a problem. If the temperature of the air downstream of the bleed air valve becomes excessive, the valve will automatically close. A warning light in the cockpit, which is monitoring the system for both excessive temperature and pressure, will come on. Excessive pressure in the system can be caused by failure of the high-pressure shutoff valve to close when required. A pressure sensor monitors duct pressure upstream of the bleed air valve. In the event of excessive pressure, the bleed air valve will once again automatically close, and the warning light will come on. In the event of either of these faults, the pilot can restore the system by opening the isolation valve, allowing the air from one engine to operate the entire system. The air in the bleed air manifold is hot, in excess of 180 degrees Celsius. So any air leaking from the manifold could cause a great deal of damage. There are temperature monitors mounted adjacent to the manifold all along its length. If any of these monitors senses an excessive temperature caused by a bleed air leak, the wing duct overheat light for the affected side will illuminate. The pilot can isolate the leaking area by closing the appropriate bleed valve and ensuring that the isolation valve is closed. In the system shown here, the auxiliary power unit air is fed into the left duct. So in order for it to supply all services, the isolation valve has to be opened. Similarly, the external air connection feeds air from an external source into the right duct. So again, the isolation valve needs to be open for it to supply air to all of the services. That is the end of the lesson. In this lesson, you have learned that most modern gas turbine engine aircraft have a bleed air system supplied with air tapped from the engine's compressors. The air is used by a number of systems, as shown here. The air supply is backed up by the auxiliary power unit, and on the ground by external air supply carts. The system is duplicated and protected from over-temperature and over-pressure. In this lesson, we will look at the sources of air for an aircraft's cabin air conditioning system, and we will examine the methods used to maintain the air at a satisfactory temperature. We will begin, however, with a short review of the makeup of the atmosphere, to explain the need for air conditioning and pressurization systems. Modern jet airliners cruise at high altitudes, up to 43,000 feet. The advantages of high-altitude flying are greater fuel efficiency, higher speed, and, on most occasions, the aircraft will be above any bad weather. The disadvantages are that there is insufficient oxygen to breathe, and the air is extremely cold. In a standard atmosphere, the temperature drops at a rate of 1.98 degrees per 1,000 feet up to the tropopause, which is at approximately 36,000 feet, or 11 kilometers. This means that on a standard day at 31,000 feet, the outside air temperature will be a chilly -46 degrees Celsius. The atmosphere is made up of 78% nitrogen and 21% oxygen, with the other 1% consisting of various trace gases. The pressure of the air at sea level on a standard day is 14.7 pounds per square inch, or psi. So the partial pressure of the oxygen will be 21% of 14.7 psi, which is 3.08 psi. The table here shows the air pressure drop with altitude and the consequent reduction in the partial pressure of the oxygen. Below 10,000 feet, the body can cope with the reduction in oxygen pressure with no harmful effects. Above this height, the effects of hypoxia begin to become apparent, although passengers sitting and relaxing will suffer few noticeable effects below 15,000 feet. Aircraft air conditioning and pressurization systems limit the maximum cabin altitude to 8,000 feet, with a cabin temperature of about 20 degrees Celsius, thus providing a comfortable environment for the crew and passengers without the need for oxygen, except in emergencies. The provision of air from a large gas turbine-engined aircraft's air conditioning system is subject to regulatory requirements, governing both the amount and the quality of the air to be provided. These requirements are laid down in the EASA Certification Specification for Large Aeroplanes, CS25, Book 1. To summarise the regulations, each passenger and crew compartment must be ventilated, and each crew compartment must have enough fresh air, but not less than 0.28 cubic meters per minute, or 10 cubic feet per minute per crew member, to enable crew members to perform their duties without undue discomfort or fatigue. Carbon monoxide concentrations must not be more than 1 part in 20,000 parts of air. Carbon dioxide concentration during flight must not exceed 0.5% by volume in compartments normally occupied by passengers or crew members. Most modern gas turbine-engined aircraft have a bleed air system, which takes hot pressurized air from the engine's compressors and feeds it into the bleed air duct. The air comes primarily from a low-pressure source, but it may be augmented by high-pressure air. On the ground prior to engine start, air may be supplied by an auxiliary power unit. One of the primary uses of this air is to supply the charge air for the aircraft's air conditioning system. Since the bleed air supply is always at a higher temperature than that required for passenger comfort, it needs to be cooled before use. The cooling is done by the air conditioning pack. In order to provide redundancy, there are 2 or more packs, fed from different sections of the bleed air duct. The bleed air flow into the air conditioning pack is controlled by a pack flow control valve. Closing this valve will shut off the airflow and close the pack down. In many installations, this valve modulates to supply a constant mass flow of air to the pack, or in some systems, there is a separate mass flow controller. Most air conditioning packs use an air cycle machine, or ACM. The machine uses the principle of energy conversion and surface heat exchange for its operation. There are 3 basic types of air cycle machine. The turbo compressor, or bootstrap, the brake turbine, and the turbo fan. We will now look at each of these in turn. Of the 3, the turbo compressor or bootstrap is the most popular air cycle machine in current use. It is used where the pressure of the bleed air is relatively low, as in the case of aircraft using high bypass ratio or small turbo propeller engines. It consists of two heat exchangers, both using ram air as their cooling medium, and a rotating turbine and compressor arrangement. The turbine assembly is sometimes referred to as the turbo refrigerator. The low-pressure bleed air, or air from a blower, is pre-cooled in the primary heat exchanger. Although the heat exchanger is very efficient, it can't cool the charge air down to a temperature lower than that of the ambient ram air, which in some situations may be as warm as 40+ degrees Celsius. The cooled bleed air then has its pressure and temperature increased by the compressor. Between the compressor and the turbine is the secondary heat exchanger, which serves to remove from the air much of the heat generated by the compressor. The pressure in the air is then used to drive the turbine. This removes the energy from the air and causes a large temperature drop. The output air temperature from the unit can be as low as 2 degrees Celsius. In order to provide sufficient airflow across the heat exchangers when the aircraft is on the ground, or at low speed in the air, a fan is provided. This fan is normally driven by the turbine, but in some cases it may be electrically or pneumatically operated. The ram air inlet and exit doors control the flow of cooling air through the heat exchanger. Their positions are controlled automatically by signals from the temperature control system. They are normally held open for maximum cooling on the ground and at low speed and low altitude. After takeoff, once the flaps are retracted, the doors will modulate as required to maintain the required pack outlet temperature. In some systems, they are automatically closed during takeoff and landing, to prevent debris damaging the system components. As the aircraft climbs, the outside air temperature cools, allowing the heat exchangers to become more effective. The temperature control valve allows hot bleed air to be added to the cooled air in order to maintain a comfortable cabin temperature. In the brake turbine system, the bleed air pressure from the engine needs to be considerably higher than the pressure required by the bootstrap system. The charge air is supplied directly to the turbine via a heat exchanger. The turbine drives the compressor, which takes in low-pressure ambient air and expels it through a restriction. This causes a back pressure on the compressor, which in turn puts a load of brake on the turbine, hence the name, and provides the energy conversion which removes the heat from the charge air. Some installations feed the output from the compressor into the ducting downstream of the heat exchanger to increase the airflow through the heat exchanger by jet pump action. This system is lighter than the bootstrap system, but unless the jet pump installation is used, it cannot be used for cabin cooling when the aircraft is stationary. The fan turbine, or turbofan system, is a refinement of the brake turbine unit, in which, instead of a compressor, the turbine is coupled to a fan of sufficient capacity to draw the required volume of cooling air through the primary heat exchanger. Therefore, the unit is not dependent on ram air for its operation and can be operated on the ground. The general design of the unit is such that it is extremely light and compact. The engine delivery pressure must be higher than for the other systems, and the turbine must be capable of higher speeds to achieve the necessary pressure drop. That is the end of the lesson. These are the main points that you should now know and understand. The charge air for a modern airliner's air conditioning system is supplied from the engine's compressors. Normally the low-pressure compressor, but in some circumstances the high-pressure compressor may be used. On the ground prior to engine start, air may be supplied by an auxiliary power unit. The temperature and the pressure of the air are controlled by the air conditioning system. The bootstrap is the most common type of air cycle machine. In this system, the charge air is first cooled in the primary heat exchanger. From there it passes to the compressor, where its temperature and pressure are raised. The purpose of this is to ensure an adequate pressure and thus temperature drop across the turbine. From the compressor, the air then passes through the secondary heat exchanger, reducing its temperature again. The air is now used to drive the turbine, which in turn drives the compressor. The pressure drop across the turbine produces a large temperature drop. The pack cooling fan is used to supply the heat exchangers with cooling air on the ground and during low-speed operation. In this lesson, we will look at the other components, which along with the air conditioning packs, make up an aircraft's air conditioning system. We will then examine how the air temperature is controlled and how the air is distributed throughout the aircraft. We will finish off by having a quick look at a vapor cycle air conditioning unit. When operating on the ground or at low altitude, the charge air entering the air conditioning pack may be very humid. When the air is cooled, this humidity will condense out as water droplets. In order to prevent it raining on the passengers and crew, a water separator is fitted in the pack downstream of the turbine of the air cycle machine. The water separator consists of two parts, a coalescer and a series of collector tubes. When the air leaves the air cycle machine, the water will be in very small droplets, in the form of a fine mist. The purpose of the coalescer is to increase the size of the water droplets. It consists of a filter, normally of coarse wire gauze. The water droplets come together on the gauze, forming larger drops before they are carried through to the second stage, where a swirl is imparted into the air. The centrifugal force throws the water drops outward. When they strike the collector tubes, they run down to the bottom of the case and exit via the water drain. The relief valve will open to safeguard the airflow to the cabin should the coalescer become blocked with ice or debris. The water separator does most of its work in low-altitude humid conditions. However, at the high cruising altitudes used by modern transport aircraft, the air is very dry. When operating at high altitudes for long periods of time, it may be necessary to increase the moisture content of the conditioned air from the 1 to 2% relative humidity of the ambient air to a more comfortable level. The component used to do this is the humidifier, a typical example of which is shown here. The water tank contains drinking water. It is pressurized by bleed air from the engines. This tank is usually referred to as the potable water tank. The water jet is fitted in a venturi tube downstream of the water separator in the conditioned air duct. Bleed air is also fed into the jet. This and the reduced static pressure of the dry air caused by the venturi effect ensure that the spray of water mist is absorbed into the air. The fabric-covered swirl vanes further ensure that the air and moisture are thoroughly mixed. The fabric absorbs any extra moisture, giving it back when the humidifier is switched off. The water supply valve is controlled by a humidistat. This is a device which can measure humidity and operate a switch when a particular level is reached. It is measuring the humidity in the air conditioning duct. When the humidity falls below a predetermined level, the valve will open, and humidification will commence. The pack flow control valve may incorporate a mass flow controller, or it may be a separate unit. The mass flow controller is fitted to ensure that a constant mass flow of air is supplied to the air conditioning packs, regardless of the engine RPM or intake air pressure. This helps to make control of the aircraft pressurization much easier. When used with blower systems, the mass flow controller operates a spill valve, which dumps excess air to atmosphere. In systems that use engine bleed air, the mass flow controller adjusts the airflow through itself, so that the required mass flow passes to the system irrespective of changes in the value of the pressure upstream and downstream of the unit. The simplified mass flow controller shown here consists of a piston with cutouts in its face and barrel, which moves inside a cylinder with matching cutouts in its barrel. When the inlet pressure is low, the spring will push the piston fully to the left, and the cutouts in the barrels will be fully aligned, allowing maximum airflow through the unit. As the inlet pressure increases, the mass flow will tend to increase. However, the increased pressure on the face of the piston will move it to the right against the spring, reducing the airflow through the unit. Thus, with pressure changes, the piston position will modulate in the cylinder, maintaining a constant mass flow to the packs. Control of the pack outlet temperature is usually achieved by mixing hot air with the cooled air from the air cycle machine. The temperature control can be either manual or automatic. Automatic temperature control is achieved by comparing a pilot-selected temperature with the actual temperature of the air. In your aircraft, you will find that the selector does not have temperatures marked on it, but merely hot and cool. However, to aid understanding, we will mark our selector with temperatures. The temperature of a sensor in the cabin is compared electronically with the selected value, and any difference modulates the hot air valve to allow more or less hot air to bypass the cooling components to increase or decrease the cabin temperature. If, for instance, the pilot selects an increase in temperature, the hot air valve will open to warm up the cabin. Once the selected temperature is reached, the valve will modulate as required to maintain it. If the manual auto switch is moved to the manual position, the hot air valve will now move in direct response to the temperature selector switch position and remain in the selected position. The pilot is now no longer selecting a temperature. Instead, he is selecting the amount of hot air to be added. The cabin temperature achieved will vary with the environmental conditions. In order to avoid large temperature gradients between the extremities of the cabin, it is often necessary to divide the cabin into zones and control the temperature in each zone individually. This control is achieved from the flight deck using zone control knobs or switches. The larger the aircraft, the more zones there will be. The Boeing 747 has 5 zones, whereas the Airbus A320 has 3. The temperature of the air delivered by the packs is determined by the zone requiring the coolest air input. This will normally, but not always, be the flight deck. Individual zone requirements are satisfied by adding hot trim air from the bleed air system to the output of the air conditioning packs. The amount of trim air added is controlled by zone trim air valves. Their positions are dependent on inputs from the individual zone temperature control systems. The trim valve for the zone requiring the coolest air will be closed. The hot air pressure regulating valve modulates to control the pressure of the trim air. If required, this valve can be closed by a switch on the control panel. Most passenger transport aircraft supply warm air to the cabin by means of floor and wall passages, and this warm air maintains the interior surfaces at cabin temperature, reducing drafts and direct heat losses, which in turn allows the entering air temperature to be closer to the cabin temperature. Recirculation fans are used to augment the air conditioning packs, allowing a reduced number of packs to be used during the cruise, which decreases engine bleed requirements and improves fuel economy, while still maintaining a constant ventilation rate throughout the cabin. The fans draw cabin air from the underfloor area through filters, then reintroduce the air into the conditioned distribution system. Air from the areas around the toilets and galleys is not recirculated, but is vented directly overboard. The ducting is in two distinct sections, to provide for separate flows of cold and heated air. The cold conditioned air is supplied to the passengers individually, through a system known as the Gasper air system. Gasper air is tapped from one of the zone's supply ducts upstream of where trim air is added. The Gasper fan provides a positive supply of conditioned air to all zones through individually controlled outlets or punker louvers. Conditioned air is supplied to the flight deck crew stations, where it can be adjusted for flow direction and quantity. It is also supplied to the flight deck windows for demisting purposes. The flight deck crew is able to monitor both the cabin and the duct temperatures throughout the aircraft. On the Airbus electronic screen air conditioning page shown here, the zone temperatures are shown, as are the duct temperatures. The positions of the zone trim air valves are also graphically displayed. The crew also receives warnings in the event of malfunctions in the system. For instance, if the temperature of the air in the trim air duct becomes excessive, the amber fault light in the switch will illuminate. The vapor cycle air conditioning system is similar in operation to the domestic refrigerator, or the galley cart cooling system used on some large aircraft. Its use for aircraft is now generally limited to small piston engine types. The system uses a refrigerant, normally Freon, which alternates between the vapor and liquid states. It is compressed, cooled, expanded, and heated in that order. The refrigerant is a liquid which boils at approximately 3.5 degrees Celsius at sea level atmospheric pressure. At higher pressures, the boiling point is increased, and vice versa. The major components of the system are the evaporator, the compressor, the condenser, the expansion valve, the receiver, and the electrically driven blowers which pull outside air into the aircraft across the evaporator. The system operates on a continuous cycle, but in order to explain the system more clearly, we will look at a unit of Freon as it makes its way around the system. The receiver, which acts as a reservoir, contains high-pressure liquid Freon. On leaving the receiver, the Freon comes to the expansion valve. This valve allows the Freon to expand, reducing both its pressure and temperature as it enters the evaporator. As the Freon passes through the evaporator, it takes heat from the cabin air, therefore cooling the cabin air. As the temperature of the Freon increases, it boils, changing from a liquid to a low-pressure vapor. The compressor raises the pressure and the temperature of the vapor before it enters the condenser. The condenser is positioned so that cold ram air passes over it. This causes the vapor to give up its heat causing it to condense back into a high-pressure liquid. The pressurized liquid then passes to the receiver, ready to begin the cycle again. That is the end of the lesson. You should now know that air conditioning systems may have a centrifugal water separator for use at low altitude and a humidifier supplied with potable water for use at high altitude. You have seen that the mass flow controller ensures that the air conditioning packs receive a constant mass flow of air throughout their operating envelope. You should know that the cabin is split into a number of zones, and that the outlet temperature of all packs is set by the zone requiring the most cooling. Zone trim valves add hot air to the other zones to satisfy their requirements. Recirculation fans are used to augment the air conditioning packs. And the Gasper system supplies cool air to individual seats. Finally, you should have learned that on some smaller aircraft, a vapor cycle air conditioning system is used. In this lesson, we will examine the pressurization control systems fitted to modern airliners. We will look at the necessary safety devices fitted and the indicating systems available to the crew. Modern aircraft operate more efficiently at high altitudes, and they have high rates of climb and descent. In order to take advantage of these properties, the interior of an aircraft flying at high altitude is pressurized to allow passengers and crew to function normally without the need for additional oxygen. Up to an altitude of 10,000 feet, the air pressure, and consequently the amount of oxygen, is sufficient for humans to operate without too many problems. However, the effects of lack of oxygen can become apparent at altitudes above this. To prevent any risk of problems due to a lack of oxygen, it is a regulatory requirement that cabin pressurization systems are designed to produce conditions equivalent to a maximum of 8,000 feet in the aircraft cabin. This means that there is no need for oxygen equipment except for emergency use by crew or passengers. The difference in pressure between the pressurized hull and the atmosphere produces stresses, which are applied cyclically every time the aircraft is pressurized and depressurized, causing fatigue, which can ultimately lead to structural failure. The airframe structure must be strong enough to withstand the differential pressures generated. The aircraft manufacturer will set as a structural limit a maximum differential pressure. That is, the difference between the pressure inside the pressurized compartment and the pressure of outside air, which the pressurized hull can safely withstand. The normal operating maximum will be slightly lower than this. On modern transport aircraft, the normal operating maximum differential pressure is typically between 8 and 9 pounds per square inch, or psi, or between 552 and 621 hectopascals. This maximum differential pressure, along with the maximum permitted cabin altitude of 8,000 feet, will set a maximum for the altitude at which the aircraft can operate. As you can see from this barometric pressure table, the air pressure at 8,000 feet is 10.91 psi. So if the manufacturer has set the aircraft's maximum differential pressure at 8.2 psi, then the minimum outside pressure is 10.91 minus 8.2, which equals 2.71. We can see from the chart that this equates to just a touch over 40,000 feet. Thus, an aircraft with a maximum differential pressure limit of 8.2 psi will have a maximum operating altitude of 40,000 feet. This is, of course, the pressurization limit. The aircraft's maximum altitude may be further limited by other factors. If the maximum permitted differential pressure is reduced by an aircraft defect, for instance a cracked cockpit window, the maximum aircraft altitude will also be reduced by the need to maintain the maximum cabin altitude at 8,000 feet. For instance, if the maximum differential pressure is reduced to 6 psi, then the minimum outside pressure will now be the pressure at 8,000 feet, which is 10.91 psi minus 6, which equals 4.91 psi. From the table, the altitude equal to 4.91 psi is approximately 27,000 feet. This is the maximum altitude limit with a differential pressure of 6 psi. The passenger cabin, flight deck, and cargo compartments are normally pressurized. The landing gear bays, radome, and the tail and nose cones are unpressurized. Cabin pressurization is achieved and controlled by having a constant mass flow of air entering the cabin from the conditioning system, and then varying the rate at which it is discharged to atmosphere. The constant mass flow of air is supplied by the air conditioning packs via their mass flow controllers, and is discharged to atmosphere through the discharge or outflow valve or valves. The position of the outflow valve can be controlled either automatically by an automatic pressurization controller or manually by the flight crew. Closing the outflow valve reduces the outflow and increases the cabin pressure, causing the cabin altitude to descend. Opening the valve has the opposite effect, increasing the outflow, reducing the cabin pressure, and causing the cabin to climb. There are a number of safety devices which must be fitted to any cabin pressurization system. The safety valve is a simple mechanical outwards pressure relief valve, fitted to relieve positive pressure in the cabin when the normal maximum pressure differential allowed for the aircraft type is exceeded, preventing the structural limit from being exceeded. This valve is totally independent of all other control systems, and will open if the cabin differential pressure rises to approximately 0.25 psi above the normal maximum. The regulations stipulate that there must be 2 safety valves fitted. The fuselage is designed to withstand the positive differential pressure produced by the pressurization system. However, it is not able to withstand the crushing forces that a negative pressure differential would produce. To prevent this problem, simple mechanical inwards relief valves are fitted. They will open if the pressure outside the aircraft exceeds that inside by 0.5 to 1.0 psi. There must also be 2 of these valves. The inwards and outwards safety valves may be combined together in one unit, or may be completely separate components. They are positioned above the aircraft flotation line, so that in the event of a landing on water, they will not allow the water to flow into the aircraft. The dump valve is a manually operated component. It enables the crew to reduce the cabin pressure to 0 for emergency depressurization. This valve may, in some systems, also be used as the air outlet during manual operation of the pressurization system. Blowout panels are fitted in the floor between passenger and cargo compartments, in order to prevent excessive differences in pressure occurring between these areas in the event of, for example, a cargo door opening in flight. The panels are normally fitted under passenger seats and they are held in place by springs. If a cargo door should open, then the pressure differential between the passenger and cargo compartments will overcome the springs and the panels will open, equalizing the pressure between the compartments before the floor structure is damaged. Some systems are fitted with a ditching control, which will close all the discharge valves in the event of a forced landing on water. This will reduce the flow of water into the cabin. There will be an oral or visual warning if the cabin altitude exceeds 10,000 feet. The oral warning may take the form of a horn, and the visual warning a red light in prominent view of the pilot. There is normally a horn cutout button which can be depressed to cancel the horn. That is the end of the lesson. You should now know that the maximum permitted cabin altitude is 8,000 feet, and that the normal maximum positive differential pressure is between 8 and 9 psi. You should understand that the aircraft's maximum operating altitude is dependent upon the maximum differential pressure, and given a barometric pressure table, you should be able to calculate this maximum altitude. You should also know that the pressurization is controlled by having a constant mass flow of air into the fuselage and controlling its exit using outflow valves. You should understand the purpose of the various safety devices fitted to a pressurization system. The positive outward opening pressure relief valves prevent the structurally limiting maximum differential pressure from being exceeded. And negative inward opening relief valves prevent the pressure inside the cabin becoming less than that outside. The dump valve is used to completely depressurize the aircraft, and the ditching control is used to close all outflow valves prior to the aircraft landing on water. Blowout panels are fitted in the floor between passenger and cargo compartments in order to prevent excessive differences in pressure occurring between these areas. And finally, an oral or visual warning will be given to the crew when the cabin altitude exceeds 10,000 feet. In this lesson, we will examine the various types of controllers used by pressurization systems. We will look at the required pilot inputs and at the indicating systems used to inform the crew of correct system operation. We will look at a typical flight profile using an automatic pressure controller, and finally, we will see how the pilot can control the pressurization manually. Pressurization controllers vary in construction and operation. On simpler small aircraft, they may be purely pneumatic in their operation. On old generation jets, they are electro-pneumatic, and in the case of most modern aircraft, they are electronically operated. Whatever type of controller is used, it will receive signals informing it of both the cabin and ambient pressures. The controller has three functions. It will control the cabin altitude, it will control the cabin altitude rate of change, and it would limit the maximum differential pressure. Old generation controllers have controls for selecting the required cabin altitude and cabin altitude rate of change. They send signals to the electric motor-driven outflow valves. On modern aircraft, most of the control is done automatically by an electronic controller. The controller receives electrical signals proportional to aircraft altitude and cabin altitude. It will then control the outflow valves to maintain a cabin altitude according to an inbuilt program. On the Boeing 737, the pilot selects the aircraft cruise altitude and landing airfield elevation during his pre-flight preparation. The controller automatically controls the outflow valve to achieve and maintain the appropriate cabin altitude for the phase of flight. On most Airbus types, during normal operation, the pilot makes no inputs to the system at all. The controller receives all necessary altitude data from the flight management computers. This schematic diagram shows the arrangement of the pressurization control system of a modern passenger transport aircraft. The automatic controllers are duplicated and have inputs from the aircraft static pressure sensing system, the cabin pressure sensors, and the air-ground logic system. If pre-pressurization, that is, pressurization on the ground prior to takeoff, is part of the schedule, then inputs are also required from the thrust lever positions. One controller is operating and the other is on standby. The roles are automatically reversed after each landing. In the event of a failure, the standby controller will automatically take over control. The controllers are normally located away from the flight deck in an electrical service center. Each outflow valve is operated by one of 3 electric motors. There is one motor for each automatic controller and another for manual control. The minimum indications required for a pressurization system are cabin altitude, cabin vertical speed, and cabin differential pressure. This information can either be presented on direct reading gauges or electronically on an LCD screen. The cabin altimeter measures cabin pressure, but it is expressed on the gauge in terms of the equivalent pressure altitude of the cabin. The cabin vertical speed indicator, VSI, indicates the rate at which the aircraft cabin is climbing or descending. The cabin differential pressure gauge indicates the difference between the air pressure inside the cabin and the outside air pressure, and is generally calibrated in pounds per square inch. In the event of a malfunction of the pressure controller or outflow valve, a high pressure reading on this instrument would indicate that the safety valves were controlling the cabin pressure at the structural maximum pressure differential. The cabin pressurization control panel is remote from the pressurization controller and will generally be fitted in the overhead panel on the flight deck. The control panel may have rotary knobs for the pilot to set the expected cruise altitude and the elevation of the landing airport. In a typical system, there are 3 modes of operation: auto, alternate, and manual. In auto mode, one of the 2 automatic pressurization controllers will be operating. The pilot can force the system to use the other controller by selecting alternate. Selection of manual will lock out all normal automatic functions and enable the pilot to control the position of the outflow valves. We will now take a look at a typical flight to see how a typical pressurization system will operate in the auto mode. During his pre-flight preparation, the pilot will set the expected cruise altitude and the landing airfield elevation. In our example, the aircraft will be cruising at 30,000 feet, before landing at an airfield with a pressure altitude of 1,000 feet. With the aircraft on the ground, the operating controller will hold the outflow valve fully open. When the pilot opens the thrust levers for takeoff, the controller will signal the outflow valve to move towards closed, pre-pressurizing the aircraft cabin into a small differential pressure of approximately 0.1 psi. This ensures that the transition to pressurized flight will be gradual and that there will be no surges of pressure on rotation. As the aircraft takes off, the ground air logic system will signal the controller to switch to proportional control. The controller will sense ambient and cabin pressure and position the outflow valves to control the rate of cabin pressure reduction, or cabin climb, in proportion to the rate of climb of the aircraft, so that slightly less than the maximum permitted differential pressure is attained as the aircraft reaches its cruising altitude. The cabin rate of climb will normally be between 300 and 500 feet per minute, with a maximum limit of 500 feet per minute. If the aircraft is required to level off during the climb, then the pressurization controller will sense this and level off the cabin. When the aircraft begins to climb again, the controller will once more position the outflow valves to control the rate of change of cabin altitude, in proportion to the rate of climb of the aircraft. The cabin rate of climb will again normally be between 300 and 500 feet per minute. When cruise altitude is reached, the controller will maintain a constant cabin altitude. There will now be a constant mass flow of air through the cabin. The mass of air coming in from the packs will equal the mass leaving through the outflow valve. Once established in the cruise, small changes in aircraft altitude will be accommodated without any change in cabin pressure. However, if the cruise altitude has to be increased significantly, then the flight altitude selection will have to be reset. If this is not done, and the maximum differential pressure is reached, the controller will not allow further increase in differential pressure, and the aircraft will now be in maximum differential control. As the aircraft climbs, the cabin will also climb, to keep the differential pressure within limits. When the controller senses that the aircraft is descending, it will switch back to proportional control and descend the cabin at a rate to produce a differential pressure of approximately 0.1 psi on touchdown. The descent rate will normally be about 300 feet per minute. When the aircraft lands and the ground air logic system switches to ground mode, the outflow valves will slowly open fully to equalize cabin and ambient pressures. On older types of aircraft, the cabin is not pressurized prior to takeoff. And, because the fuselage is not designed to absorb the landing shock simultaneously with pressure differential forces, the cabin is completely depressurized just prior to landing. With the system under manual control, the outflow valve position can be adjusted by operation of the manual open-close switch. The pilot now controls the differential pressure, cabin altitude, and cabin rate of climb or descent. On the system shown here, a placard along the bottom of the control panel shows cabin altitude against aircraft altitude at maximum differential pressure. The pilot can consult this in order to establish the cabin altitude required for any given aircraft altitude. Opening the outflow valve will cause the differential pressure to decrease, the cabin pressure to decrease, and the cabin altitude to increase. The cabin VSI will show a climb. Closing the outflow valve will cause the differential pressure to increase, the cabin pressure to increase, and the cabin altitude to decrease. The cabin VSI will show a descent. Cabin rates of climb and descent should be carefully monitored, and should not normally be allowed to exceed 500 feet per minute during the climb, or 300 feet per minute in the descent, in order not to cause too much discomfort for the passengers. That is the end of the lesson. You should now understand the relationship between cabin pressure, cabin altitude, and ambient pressure. Remember, in level flight, if the outflow valve is opening, The cabin vertical speed indicator will show a rate of climb, the cabin altitude will increase, and the differential pressure will decrease. If the cabin altitude reaches 10,000 feet, then an oral and/or visual warning will be given to the crew. Similarly, in level flight, if the outflow valve is closing, the cabin VSI will show a rate of descent, the cabin altitude will decrease, and the differential pressure will increase. If the maximum differential pressure is exceeded, then the positive pressure relief valves will open. Finally, remember that if the pressurization system is in the manual mode, the cabin altitude, the cabin rate of change, and the differential pressure are all controlled by the pilot operating an outflow valve manual open-close switch. In the Ice and Rain series of lessons, we will examine the methods used to detect when an aircraft is flying in icing conditions. And we will look at the various systems that can be fitted to aircraft to prevent ice and rain becoming a problem. We will not be discussing pre-flight ground de-icing. This is covered in the Operational Procedures series of lessons. In this lesson, we will first quickly look at how ice forms, and then we will look at the various systems that can be used to detect icing conditions and give a warning to the pilot. Icing on aircraft in flight is caused primarily by the presence of supercooled water droplets in the atmosphere. If the droplets impinge on the forward-facing surfaces of an aircraft, they freeze and cause a build-up of ice, which may seriously damage the aerodynamic properties of the aircraft. These droplets can exist in the temperature band from 0 to -40 degrees Celsius. Below -40, they are already frozen and will not stick to the surface of the aircraft. The actual amount and shape of the ice buildup depends on the surface temperature and the size of the droplets. A full explanation of icing conditions is given in the Meteorology series of lessons. You should expect ice to be a problem whenever the temperature is between 0 and -40 degrees Celsius, and visible moisture in the form of clouds or rain is present. Ice detection systems can be split into two groups: those which sense a build-up of ice, known as accretion-type systems, and those which sense, by measuring temperature and humidity, when icing conditions are present. These are known as inferential-type systems. The simplest of the accretion-type detectors is the pilot's eye. He may be able to see ice beginning to build up on such things as the leading edges of the windscreen wiper blades. Some aircraft may have lights to illuminate the wing and fin leading edges, plus the engine intakes to help the pilot monitor for the build-up of ice at night. On some aircraft, the pilot's eye is the only ice detection system. To assist the pilot, some aircraft have a device known as the Teddington ice detector. This detector consists of an aerofoil-shaped mast protruding into the airflow, which is visible from the cockpit. The mast incorporates a heater element and a light to illuminate the mast at night. When icing conditions are encountered in flight, with the heater power supply switched off, ice accumulates on the mast and gives a direct visual indication of ice accretion. The heater may be switched on for a short period to dissipate accumulated ice. The more quickly the ice reforms, the more severe are the icing conditions. The Smith's ice detector is another accretion type of detector. It consists of a hollow tube, attached to the aircraft by one end, sitting in the airflow. It has holes drilled in the leading and trailing faces. There are 4 holes in the leading edge and 2 in the trailing edge. In flight, under normal conditions, the air enters the 4 front holes more quickly than it can exit by the rear 2. This causes a pressure build-up in the tube, which is sensed by a capsule connected to its base. The capsule expands, keeping a pair of electrical contacts apart. In icing conditions, the leading edge holes become blocked by ice, and the pressure in the tube falls. The capsule contracts, causing the ice warning light to illuminate. There is a heater element fitted around the tube to melt accumulated ice. Once again, the more quickly the ice reforms, the more severe are the icing conditions. The English electric or Napier ice detector is a mechanically operated accretion type of detector. In this detector, a serrated rotor shaft is continuously driven by an electric motor. The shaft rotates adjacent to a fixed knife-edge cutter, with a clearance between them of less than 0.02 of an inch. The unit is mounted on flexible mountings on the side of the aircraft fuselage, with the rotor shaft protruding into the airflow, with its axis at right angles to the airflow. The cutter is in the lee of the shaft. Under normal conditions, little torque is required to drive the rotor. In icing conditions, ice builds up on the rotor and is shaved off by the cutter. Shaving off the ice requires greater rotational torque and causes the motor to rotate slightly in its flexible mountings. This movement operates a micro switch which gives an ice warning. The warning remains as long as ice continues to foul the cutter blade. The Rosemount ice detector is another mechanically operated accretion type of detector. It consists of a short cylindrical probe positioned in the airflow, mounted on a vibrator housing, which vibrates the probe axially. If ice builds up on the probe, the added mass reduces the frequency of the vibrations. When the frequency falls to a predetermined level, an ice warning is given. When the ice warning is given, a built-in heater element heats the probe, which melts the accumulated ice, allowing the vibrating frequency to return to normal and the warning to stop. After 6 seconds, the heater switches off and the icing cycle recommences. The frequency of the cycle may be measured to give an indication of the ice accretion rate. The final accretion type of ice detector that we want to look at is the beta particle detector. This is the most modern type of detector. It has no moving parts. The detector consists of 2 probes, mounted perpendicularly from the forward fuselage. The forward probe is an emitter, which emits beta particles. The rear probe is a beta particle detector, which detects the level of particle transmission from the front probe. Beta particles are absorbed by ice, so that, in icing conditions, fewer particles are sensed by the detector. At a certain beta particle count rate, corresponding to approximately 0.4 mm of ice, a relay in the detector probe will operate, causing a warning on the flight deck. Ice can only be formed when there is a combination of moisture and freezing temperatures. In the Sangamo Western ice detector, these 2 conditions are detected separately, and therefore icing conditions are detected rather than actual ice formation. This then is an inferential type of ice detector. The system comprises 3 main components: a moisture sensing head, a moisture detector controller, and a thermal switch. The moisture sensing head consists of two heated metal resistance bulbs situated in the airflow and arranged so that the leading bulb screens the rear one in such a way that no moisture impinges upon it. When the detector encounters moisture in the airflow, the shielded rear bulb remains dry and cools at a slower rate than the wet leading bulb. The moisture detector controller is situated in the base of the unit and senses the temperature difference between the wet and dry sensing bulbs. When the temperature difference reaches a predetermined value, it will send an icing conditions signal. The thermal switch is a contact operating thermometer which is housed in a bulb and is exposed to ambient temperature. With a temperature below freezing, the thermal switch will send an icing signal. If both the moisture detector controller and the thermal switch are sensing icing conditions, then an ice warning will be given, or the automatic anti-icing or de-icing cycles will be initiated. That is the end of the lesson on ice detection. You have seen that there are two types of ice detector. The accretion type, which senses actual ice build-up, and the inferential type, which senses when the aircraft is in environmental conditions where icing will occur. You will find that on many modern aircraft there is no ice warning system, or perhaps just the Teddington type of visual indicator. So an awareness of the in-flight conditions with regard to temperature and moisture is essential for all aircrew. In icing conditions, the first signs of ice build-up can usually be spotted on aerials or on the windscreen wipers. In this introductory lesson to ice protection systems, we will list the systems and components that need to be protected from ice and rain, and we will list the protection methods used. In the following lessons, we will discuss the various protection systems in greater detail. The following systems and components need to be protected from ice and rain. The engine air intakes and compressor inlet guide vanes need to be protected, as do the wing leading edges, along with slats if they are fitted. On some, but not all aircraft types, the fin and tailplane leading edges are also protected. Propellers can suffer from icing and need protection. Wastewater outlets and water lines in unheated parts of the fuselage will freeze up in flight any time the temperature is below zero, so they need to be heated. Any probes sticking out into the airflow, such as pitot heads and alpha probes, are susceptible to icing and need to be protected. These small components are usually electrically heated. Finally, cockpit windows need to be protected from both ice and rain. Ice protection systems normally use one of two different approaches to the problem. They are de-icing, where ice is allowed to accumulate prior to being removed, and anti-icing, where the object is to prevent ice from forming. The methods used for ice protection can be split into three groups. They are mechanical, using expanding rubber boots; thermal, with the heat being supplied by electricity, engine oil, or hot air; and liquid, using freezing point depressant fluids. These methods are all examined in detail in the following lessons. That is the end of the lesson. You should now know which surfaces need ice protection. You should know that de-icing involves removing ice that has built up, and that anti-icing is used to prevent the formation of ice.